Hi, Frontier.
All right. Can you hear us?
Yes,
Yes.
and we see you.
All right. So, do you guys know how to share your screen from a Zoom meeting? So you go share screen, and then you can do a specific tab, or you can do the whole window or the whole screen. I would just do the whole screen. Once you're ready. Ready? Sure. Presentation.
Yes, we see your screen. And Nancy is on, Nancy Hall is with us too. And we have um, Glenn Johnson, who is Nancy Hall is your regional manager. We have Glenn Johnson, who is the design and prototyping manager, who comes up with most of these projects that people at NASA and astronauts help him um, design and say they need.
Okay.
And we have Mike Bennett on also?
Looks like, oh, Mike.
Yes. Yep,
Okay.
he's there.
Team, are
So
you
we're
ready?
we're all here. So go for it, Frontier.
All right. So basically, been gone through a couple designs. We've kind of finalized this kind of style that we're going to go with. It's kind of just going to be it's going to be based on spring propulsion, and it's going to be like held together by like some sort of pulley system. And when the springs compress, it's going to be able to release it and just break off into two parts so that it'll launch up in the air but be held together like by the string or whatever. It's kind of like right here where it'll split off, be like one component and then split off into two. Let's see. Um, so we the biggest challenge I think for us personally was deciding how to get it to launch into different directions. So we kind of came up with this design where it would have a movable counterweight system like it has in like big working cranes, and there would be like angled parts to the bottom of the robot. So you shift the weight to one side and it'll tip it off into one angle, and you can bring the weight back and recenter it, if that makes sense. Um, yeah, that'll just allow for varying directions, so it's not just going to launch straight up and straight back down. Yeah, the counterweight's just going to move along like these like roller coaster style tracks inside the robot. So it'll just be able to move from one end to the other end, back and forth, controlled by like a controller of some sort.
Okay. And so the bottom piece that you're showing me is the pusher plate that's going to be in contact with the ground. Is that right?
Yes.
Okay. And then um and then it looks like the top is it going to contain the motor for pulling the two halves together? Is that right?
Likely, yeah.
Okay. And so so the rails that you've got is to reposition the mass so that you can direct the jump. Is that correct?
Mm-hmm.
Okay, very good. What do you have on your next slide?
So for the next slide, I was looking into different ways to compress and release the springs to allow it to jump. So so far, this is the best design I could find. So it basically is two springs on each side, and they're connected um, to one piece that has a pin in the middle, and the pin follows a track on the cylinder that rotates, and as it rotates, it's able to compress the springs and then eventually release them while keeping it on track so it can just keep rotating. And
Can you on your screen right now, you've got me kind of positioned over it. Can you change the position of where my there you go. That's better. Thank you. Okay, so spring barrel. Path to follow. Okay, very good. Now, have you guys tried this out at all?
No, we were going through a couple of different designs, but so far last minute we found that one and
Okay.
and
What about so have you guys gotten any springs so that you can kind of try these things out?
um
I ordered like one set of springs just like as like a reference for like designing like how big we want it. But like we haven't really done like full testing of how much force it's going to actually exert.
Okay. And part of what I'm looking for is just um you want to test out some of these plans just so you can find out which ones work best. And sometimes so you ordered some springs. Do they have the kind of compressibility that you want?
Yeah, they do.
Okay. And so they're around the correct size. Is that right?
Yeah, that's kind of what it's based off now.
Okay. That sounds great. Have you printed that base plate yet?
Um, Not fully yet. I mean, mainly I've just been kind of figuring out like exactly how I want it to be before we print out like a full bottom plate and then have to redo it.
Sure. And so part of what I'm suggesting, that bottom plate, it kind of looks I'm looking for ways that you can test out some of your stuff without spending a lot of print time and things like that. So, for example, that bottom plate looks a little bit like the lid of a uh, like a Tupperware lid or something like that. Could you could you take an old Tupperware lid and see if you can manipulate, put some of your springs on there and be able to test out how it jumps or not?
Yeah, that's it. I didn't actually think of that before.
And it just gives you a way to begin some testing before having everything printed. Um, and yeah, that's actually not bad. Take a Tupperware bowl and lid and just flip it over and be able to assemble some of that. That might give you some of the rest of that of your design as well. Does that make sense?
Yeah, it does.
Ah, okay. Now Tupperware is kind of flimsy, but it's a beginning, right? And so you might be able to just practice out with some of that. Um, Now on the right hand side, I see that you've got a little drawing. Can you explain that one a little bit better? I missed it because our
One
picture
right
was.
here.
Yeah, tell me about that.
So this is just to show one of the directions. And in the final design, it's likely going to have four sets of tracks moving in all four directions. So it's going to be able to move left, right, up, and down.
Okay.
This is just to show one direction for now.
Okay, I get you. Huh. No, that makes sense. Um, and so it's not a curved bottom, it's a slanted bottom. Is that correct?
Yeah.
Yeah. And so that gives you more of a flat face to be able to push with.
Hmm.
Huh. That's interesting. Very good. Okay. What do you think your next step is? What do you want to do as your next move?
Um, I think the first thing I'm probably going to do is probably finalize what I want this to look like and then actually start printing it out. And then as that's going along, maybe do your Tupperware idea and just see how it reacts.
And that sounds good to me. I like where you're going with this. Um, yeah, okay. I like it. Any other thoughts or questions for us? Oh, did I get lost?
No, we're just talking amongst yourselves for a second.
Oh, okay. Um, Now what about the controls? Where do you want to place the controls?
Um, Ideally, it could be housed all in the top or like underneath the tracks, possibly. So like we could have like a little like barrier that separates the bottom into two halves. So like
Okay.
your components are underneath the weights.
And where do you want to put the camera?
Um, right here I mentioned, since all the weight from the counterweights and everything is going to be on the bottom, likely in its projection, it's going to be able to re-upright itself onto that heavy weight side. So the camera will be pointing straight down.
That makes sense. And so positioning it, um, I don't know. So does that put it in the top section or the bottom section?
I think that would likely put it in the bottom section.
And I think that's smart, and it gives you a better view of the ground that way. So I think that's pretty cool. Okay. So, um, have you started looking at motors and things like that?
Um, I've just been using some of these like I mean, right here, there's a few. It's just like
Oh
these
yeah,
little
show me that. Stop sharing. Let me see what you got. It looks like a geared motor. Is that right?
oh, you can stop sharing this. Yeah. Yeah, it's like this thing where it has like two arms on each side.
And I think that's a great beginning. Now, what kind of controls does that have? Is that just a forward and backward, or is it?
Yeah, it's forward and back.
Okay. I think that that could work just fine. Um, because it's got two shafts, right? One on each side. Is that correct?
That's correct.
But they're not independent. They both go and they rotate in the same direction. Is that correct?
Yeah.
Okay. Yeah, that's all right. I think that you can do a lot with that, especially if you want to have two springs. It can kind of compress both springs at the same time. Okay. No, I think it's looking really good, team. I think you're getting some testing in is probably going to be a great way to just help you get a feel for how the springs do or don't work for you. And there's always going to be a little bit of change in that. Um, Now, just a thought. At first, I think I would spend a little bit more time on the jumping mechanism rather than the directional positioning. Does that make sense?
Yeah.
And just plan on that a little bit later. But and then also trying to decide where in that top section, how do you want to position all of, whether it's um, the motors and the batteries and things like that, because that can really centering it up so that you've got good mass in the right places is what you're looking for. Okay.
Mm-hmm.
Good job, guys. Any other thoughts, questions?
I don't think so, no.
All right. Flo, you got any comments for him?
No, I appreciate you working on it. And these teams are not doing it for a class, right? You're doing it on your own, volunteered work after school.
That
So it's really impressive what you're doing right now, and we
that's exciting.
appreciate you. Yeah, I like the shape of your robot. I'm excited to see what it will finally look like. Nancy or Mike, do you have any comments? And you have another
No,
team coming, right? Do you have another robot team?
No, so Flo, I sent you and Nancy that email about how the teams got restructured.
Okay.
It's our only jumping team.
Okay.
Okay.
Good.
Yeah, no, Glenn covered all the comments. I
Same for me.
like the design and everything. But yeah, no, that was good.
Yes.
Great presentation, guys. Thank you.
Yeah.
Hey,
Okay.
guys.
Thank
Hey,
you
team.
so much. And you guys have a wonderful afternoon there.
One
Great. Thank
more
you for your
thought for
time.
you, team.
One more thought from Glenn. And you can
Hey.
stay on.
Do you guys have any Legos?
I do, yeah.
You might be able to use some Legos to help out with some of that modeling. Does that make sense?
Yeah, it does, yeah.
Check that out. It could just make things a little bit easier. Excellent job, team. Keep it up.
Thank Thank you.
Thank you.
Awesome. All right. So this afternoon, or if it's still not afternoon, except in the East Coast, we got Bozeman, and I don't think they're on. Whose help? I'm not sure who help is.
Because which one?
There's a
Somebody.
help. There's a one that says help.
Yep,
I
it's
think
gone now.
it's gone
Yeah, I don't
now.
see it. Yeah.
Yeah,
Oh.
it's gone.
It was the
Ah.
Beatles. They were trying to get in.
Could that have been HHH? Which one was?
No, it was-
HHH was this morning.
Oh, okay.
So
So we're done with the.
Yep, we're done until 10:30 my time, 12:30 your time, when
Okay.
Bozeman in Montana will come. And then Bergen County is going to do all of theirs. And then Fairport in New York.
Okay. And then Cortland is not doing theirs today, correct?
Right. Cortland will do it next week, Nancy, with you.
Okay. So all the ones here with Cortland, I can delete that one.
Yep. I deleted Cortland. They needed the extra time, but actually Glenn did a really good job with them.
Yeah, I
week.
scheduled something for them next week. Okay, one of my meetings got pulled in here. So I'm gonna just send them the invite for that. I think I scheduled it the 9th. So yeah.
Yeah,
All
that
right.
would be good.
All right, sounds good.
All right, thank you. Thank you.
Okay.
We'll just wait for Bozeman. And hopefully they'll come maybe a little early, because Bergen, I know, has to leave school by 2:00, and I have them scheduled until 1:45.
Okay.
So
All right.
Okay.
Sounds good.
All right. So
Okay.
we've got about a half hour. Is that what you're telling me?
yep.
Okay. Sounds
Yes.
good.
Thank you so much.
Yeah, I'm probably
Sounds
gonna jump out. I don't know if I can do them, but yeah, if I can, I'll jump in.
Awesome.
Sounds great.
Okay.
I'll see
Thank
you.
you. Bye. Have a good afternoon, everyone.
And me and my partner Quinn are working on the jumping robot. And it looks like they're on their way. So yeah, we had a bit of a rough start on our project. Originally we thought we would be working with the other school that's in our district. And it would be us two and then 4 other people. So we'd be able to split up all the work. We kept reaching out. However, at one point they pretty much just stopped responding. So about a month in, we were like, all right, this isn't gonna work. So we broke off and had to kind of restart.
That's okay. And, communication is a difficult thing. I mean, you can have people in the same office and they have a hard time communicating. So I get it.
Yeah.
How are you guys doing now, though? Do you feel like you're making some good progress?
Yeah, definitely.
Excellent. That's great. So how many total in your team?
2.
Excellent. Okay. Tell us about it. What are you guys working on?
Well, we have some prototyping stuff that we've been working on of combining the body and the legs into a singular design.
Hit control and then the right arrow.
Yeah.
This is what we have right now. The idea is for this to be able to compress and jump. It's not quite working yet. Then this string, there would be eventually a type of something that would pull this down to compress the structure. And all the electronics and other things would be kept in the middle, where there will eventually be some kind of tube or something to put them all in to protect them. Yeah.
Did you share the? Yes, we did. Okay. Hold up. These.
Just very carefully, like mouse up towards the top. There you go.
Now, what did you make your prototype out of? That looks like a lot of wire.
Yep, it's made out of some wire and then also a cut up plastic tote.
Okay, very good. And right now it's a representation, but it gives some of the idea and allows you to start playing with how you want to position other things. So I think that's great. Wow. Okay, I see some of your idea here.
Mhm.
Now in yours, in your prototype right now, you only have four kind of legs, and here you've got several more. Are all of those going to have springs or not?
We'll see. I'm still working on building them all. It's going to kind of depend on how many it actually needs.
Okay.
I don't want to add extra weight if it doesn't need it.
Okay. All right. And now in some of the videos, they didn't use springs as much as they used carbon fiber, and you chose to go a different direction. Why did you choose that?
Mainly because at least at this point, this is an easier thing to prototype with for us.
Okay.
And we could probably potentially switch it at some point in the future, but this is what was easiest for building it to at least start seeing if the ideas would work.
Okay. Now tell me a little bit about what's in the middle there. How are those some of your controls and other springs, or what are you thinking about?
So what would be inside is some sort of clear, probably plastic container that would hold all of our electronics, so they would be protected from the dust that could get in, but it would still allow for the camera to take photos through it.
That's a cool idea.
Yeah. The idea with the parts you see right here is that this container would be able to move around in the body and possibly even out of the body to allow the camera to take the best pictures possible.
Okay, very good. And okay, so just as a thought, just because you're still doing early prototypes, have you thought about like a drink bottle as that central core in the middle?
That might be a good way to.
That is a really good idea.
We were
Okay.
thinking of trying to 3D print it, but that sounds a lot better.
Yeah.
Sure. And then that box that goes around it. What were you thinking about for that?
That would probably have to be 3D printed because it would have to fit snugly around that piece, and that would be the mechanism that would help compress this, and it would be kind of like a little winch-esque system. Haven't quite figured out how it would work yet, but
Okay. So, and let me see if I understand. So you're saying that's where the winch system is. Is that what that rod is that I see in the middle?
yes.
Okay. And so are you going to have two strings that are pulling at the bottom of it? Is that correct?
Yeah, that would be the idea of those two strings then pull and compress the structure. It'd probably be completely flush against one of the sides of it when fully built out, but yeah.
Okay, I'm into that idea. I think that's pretty smart. Okay, and that means that it could pull up on the bottom so that it matches up with the bottom of your transparent location, right?
Mm-hmm.
Okay, I think that's pretty smart. Okay, have you started looking at how about like some of your electronics or anything like that?
Not a ton. We did look into a bit of the self-writing and how we would be able to do that quickly so that the robot is able to reset and jump again as soon as possible. Yeah. So we did a little prototype with a robot that will be able to self-balance just to get used to the kind of code and the kind of boards and technology that we might need. That also helps us see how big we have to make the container to allow all the electronics to fit. We, about a week ago, ran into the problem of the battery wasn't producing enough energy to run it. So we're at a bit of a roadblock there, but.
Okay. What size battery are you looking at?
Oh gosh. It's a It was a 3.7 volt lithium battery, I think.
But that battery might have also been dead because it had been sitting in a cabinet for a while.
Who knows how long?
Probably very likely. So that may not be an issue. It's just a matter of getting it charged back up.
Yeah.
Okay. So first of all, I bet, although you can use the chip, the computer board that you've got on that robot, probably, you may not need that big of one because, and so you might be able to plan for a little bit smaller. I see a lot of people are going after a Pi Zero, which is pretty small, but it still has plenty of power to run small cameras.
That's good.
Now, do you have access to any of these electronics besides this robot?
We are currently trying to brainstorm which ones we think will be the best purchase. Some of the cameras that we're looking at specifically were some tiny home security ones or game cameras because they already have a Bluetooth connection. They're very durable and temperature resistant. And most of them can run off of fairly low power.
Okay. You might go to Spark Fund. Write that down. Oh, are you already familiar with Spark Fund?
Yes.
Excellent. Okay. And just so you know, they also have the programming code for a lot of their hardware.
Thanks.
And so it's just a matter of looking through and finding that. And that way you don't have to be the one inventing everything. Okay?
Yep.
Excellent. Now, you it looks like you've taken some wire to represent your springs. Have you started looking at springs themselves for what you want to do?
So far we're what we found works best. Let's see if I can get this over here. Is this piece right here is a piece of a cut up plastic tote, which honestly has had the best spring of any material we've tried so far.
Oh, very good. Okay.
Prototyping it. Yeah.
So I think we'll probably go more along those lines. Some
maybe,
sort of plastic material.
Maybe with a metal frame just for durability.
Well, and that's okay, but I mean, in terms of what type of springs did you want to look at?
Mainly like kind of tension system.
Okay. If you go to the hardware store and go to one of the people and say, "Hey, I'm doing this project for high school and I need some springs," they will walk you over to this bin where it has like 20 drawers, and each of the drawers has 20 different kinds of spring in it. And you can sit there and play with them and stretch them and push them and pull them and twist them, and it'll help you find the one that fits for you. Does that make sense?
Mm-hmm.
And typically you can get those for just a few dollars or something like that. Is that okay?
Yeah, we'll take a look into that.
Okay. No, I like what you're doing there.
Yeah, I'm gonna pull this up.
Oh, I see.
We're not missing anything.
Yeah.
Like this.
Yeah.
That didn't work. Okay, there we go.
I'm like, you know this better than I do.
There
Okay.
it goes. I see it.
We just made this slide deck just to make sure we don't miss anything. These are just like the main things we've been looking at. Yeah, we can probably get through this pretty quickly because I think we already talked about most of that.
Talked about that.
Very good.
Those are some of the home security cameras that and such
Sure.
we're looking at. And this is one of the last big ones of how to regulate the temperature of the system, just with the massive lunar temperature swings.
Very good.
Yeah, and I think we're kind of wondering which of these, like, what ways you think would work best to be like both effective and affordable and applicable to a small design.
And so in terms of thermal?
Yeah.
Wow. Okay. And I'm not as good about thermal as I would like to be. Your spray coating is probably a pretty good idea. How about this? I don't want you to worry about thermal right now. Right now, I want you to try to make it work for the environment that you're in, and then as we get closer to something that might fly or something like that, then we'll start talking about that. Does that make sense?
Yeah. I'll pull out my notebook because I did a little thing. That sounds right.
You're asking the correct questions, though. That's actually really smart.
Yeah. And you don't have to build your robot out of material that you want. Do research in what material could withstand the temperatures and just tell NASA engineers, well, they should use this material. You find any material that is handy and not costing a fortune, but do the research.
I will be right back.
Oh, okay. Sounds good.
They're just going to grab their notebook. Yeah.
And we got Bergen County on too. Hi, Emma.
Hi.
We're just finishing up with the Bozeman High School in Montana here.
Should I get it? It should be. Okay.
Okay, what do you got?
So this was some stuff that I looked into pretty recently, so not a lot of it is on the slideshow. But I was looking into some stuff to make the self-writing process use even less of types of electronics. So it is upside down. Love that. So I did research into, I don't know how to pronounce it, but it's a shape that has one stable equilibrium and one.
I like it. I've been watching some stuff and thought about that earlier today. So that's very smart. Tell me more.
And so we were thinking about an idea that was it was in the video where we were talking with someone who did NASA Hunch before. It was one of the videos that was presented by NASA, talking about a previous NASA Hunch individual's opinions and thoughts on the idea. And he brought up the idea of kind of having like spines or little legs that would help minimize the damage caused to the robot itself during the repeated collisions. And I was thinking about that idea and if it would be possible to cut those legs. We were thinking about using zip ties for prototyping, cut them to different lengths so that it would help the robot right itself. So I looked into both this shape and just the way it's oriented with a lot of sections of concave surfaces that meet at certain points, as well as looking into an idea that is often brought up when talking about this shape, which is types of tortoises that have such tall shells that they can't use their legs to right themselves. And it's a very similar shape and feels almost more applicable to the project. So I did just a little sketch of a design where all of the zip ties would be around, they would be shorter on the bottom and taller on the top so that we could have the additional benefit of the mass being a little bit lower. And then they could be cut so that it would, from whatever position it landed, it would immediately try to right itself back to the way that we want it to launch.
I think that's a terrific idea. I like where you're going with that.
Yeah.
And the idea of using some zip ties for that, I think, is also pretty smart. That's some good thinking.
Yeah, keep that up. Keep researching that one. That should be really good.
Yeah. That's the spirit I had. I was like, I gotta pull this out.
Yeah.
All right. Excellent thinking, team. I like it a lot. Good job.
Yeah. Keep up the good work there. Appreciate it.
Thank you.
Thank you.
You can always send questions anytime.
Awesome. We probably will at some point.
Okay.
Excellent.
Well, you have a great afternoon there. We appreciate your work. Bye-bye. All right, we're ready for Bergen County.
Hi.
Hey, how are you doing?
Pretty good. How are you guys?
Very good.
Okay, so we're just gonna share our screen here.
Can we share our screen?
Yeah, stop sharing. Yeah, there we go.
Excellent.
Is this what it's showing?
Oh no, is it showing this?
Okay. We see your screen. Power Systems sub-team.
Power Systems. Okay.
Okay, so I'm Emma.
But make sure we can scroll.
Sorry, we have dual monitors right now, so we're trying to figure it out.
Maybe you just tap on the screen.
Oh yeah, okay, now how do you go back?
Yeah, that worked.
Ooh. Okay, hold on. Let's just start here. Okay. There we go.
Okay.
So I'm Jabril.
I'm Emma, and we're the Power Systems sub-team for the Lunar jumping robot. So our table of contents, we're going to define our problem, research, brainstorm, develop, prototype, and future ideas that we have. So first, for define the problem, this is our overall problem statement for our entire team. So NASA needs a way for robots to travel efficiently across uneven and hazardous surfaces on planetary bodies. Current systems cannot reliably move over rocks, craters, or other obstacles, which limits exploration and data collection. NASA has prompted us to address this challenge by developing jumping robots that can overcome terrain and atmospheric barriers, take images, and reach areas that are otherwise inaccessible. So for our sub-team specifically, we have our own problem statement, which is to create a solar panel battery and charging subsystem for a lunar surface jumping robot, capable of withstanding repeated jumps/land cycles, reliably harvesting power from low-angle sunlight at the moon's south pole, while maintaining minimal mass and enabling the robot to perform frequent jumps, operate its camera/transmission system, land safely, and reset for subsequent jumps.
Okay, so next we're going to go through a bit of our research process that we had. So some of the research topics we went over was the recharge time, which is how long it takes for our solar panels to actually recharge before it can be used again. Light sensors, so we looked into a bit of sensors which would move our solar panels depending on where the light source is. Panel conditions, so these are other things such as other things regarding the positioning. So we thought of ways we could move move our panels. And next we have moon environment, which is just the way that the moon's environment would actually affect our solar panels, such as moon dust and other weather things that would be on the moon.
And then we started brainstorming. So this was our first 3 main topics. We looked into flexible solar panels, which is all the way on the left, and these would basically around an entire frame or a box of some sort. But then we weren't sure how that would work in terms of the moon's south pole. So we were looking at different ways to angle solar panels. And then we did that with the picture in the middle is a motor, which uses light sensors to move the solar panels based on the way the light's facing, which is the solar panels represented by that piece of cardboard there. And then we also looked into gimbals, which is the bottom right corner. And ultimately that would just keep the solar panels upright and straight so that while the robot was jumping, it would still be facing upright towards the sun. And overall, we decided to stop going forward with that idea, mostly because a gimbal would be really complicated for this project, and because it's not necessarily that the solar panels are straight upright, but more so that they're at the correct angle for the light. And then these are some sketches we made. We were also thinking about snaps for the solar panels shown on the right, that we would snap these onto the body of the robot and they would be facing the light.
Okay, so now we're going to go into a bit of our development that we had. So this sketch here is our pretty much main sketch. Our body team developed an idea to basically have our robot jump. So our idea was to have 2 mechanisms on each side covered in solar panels, which would allow also us to have space to hold our battery pack within the actual hubs on the ends. And we also had a mechanism to deal with our moon condition, which would be a roller brush
Lost
mechanism.
your sound. Is it my fault?
Oh, it might be, there's airplanes flying overhead.
Can you still hear us?
Can you hear us?
Now I can hear you. I don't know what.
Okay.
Okay, so also I was saying, so we have our hubs on each end, which would be covered in our flexible solar paneling systems. And within each hub would be a battery pack, and we'd have some space to allow wiring to go through it. And also we have a roller brush mechanism that you can see in the bottom left and the bottom right here, which would allow for us to deal with our moon conditions, such as moon dust and other factors that we'd need to clean off of our solar panels. So we had brushes, we thought of brushes that would spin around and clean our solar panels.
So this is a prototype that we made. This one, we modeled this in CAD and then we printed it. We did a scaled version, so this one's pretty small. But this was our like first like official prototype. Oh. So this is our prototype.
This is the printed version.
Yeah, the printed version.
Oh, very good.
And then
Okay. So some future ideas that we came across was piezoelectric materials. Since we do have a jumping robot, I thought something such as piezoelectric would be very useful. So just to go into some background, piezoelectric materials are substances that generate an electrical charge in response to applied mechanical stress and vice versa, making them essential in various applications such as sensors, actuators, and energy harvesting devices. So in an idea such as a jumping robot, seeing something that generates power when compressed, I thought that this could be a very good idea, maybe that we could look into in the future. And I'd love to get your guys' feedback on it too. Okay. So these are just some possible piezoelectric materials, which is PZT, which is lead, zirconate, titanate, which is has very high piezoelectric output. It's a bit rugged though. And then we have PVDF, which is polyvinylidene fluoride, which has flexible films and is very good at sensing impacts.
this was another future idea that we had where instead of having everything on the inside to store the battery pack, we would put the brush on the inside and that it would come out through the top and spin around so that this way there would be less moving parts on the outside of the thing because we were worried about the conditions of the robot jumping up and down. So this is what we're currently working on as of right now.
Okay.
And that's it.
And that's all.
Okay. And so stop sharing and show me what you've got there. So it sounds like you've got one of two cups. Is that correct?
Yeah, the 3D printed cups.
Yeah, yeah. So do you have both of them or what?
I can grab it.
Yes, she'll go grab it really quick. It's basically it's just one we 3D printed one of the actual cups and we 3D printed a lid for it. Where it's not exactly to scale of what our robot's going to be, but there's a lot of factors that's restricting us from the other teams, such as like how much power we're going to need to generate, and also like this general sizing of the robot. So right now we're just working on generating concepts, and then we're going to work on the specifics later.
And I think that's great. Okay.
Okay, so she has the cups right
there. Okay. Now, and you were talking about using how do these, you had wires that kind of go around it. How do they attach to that cup?
Okay, so the wires that go around, that's our jumping mechanism actually. So we're planning to kind of just attach it all on one side of the rope of the actual cylinder. Yeah.
Sure. And how do you want to attach them? Are you going to have holes in there and then you bend it through, or what are you thinking about?
We were planning on attaching it just like straight, like drilling it on, I think, because the base of our robot is a flat, like hexagon shape, I think, right now.
Okay. And part of what I'm thinking is that on your next print, you could print holes in your cup to help it be exactly where you want them, that kind of thing. Now, how many pieces of wire were you going to have around it? Was that 8 or what were you thinking?
It's depending on our body team and our jumping mechanism team. They're still trying to get through that part. But I guess depending on however many they use, that's probably how many we'll just adapt to.
Okay. And part of my thinking is also you might want to increase the thickness of it right where the wire comes in contact. That way it's a little bit sturdier for that. Now, and so once is it jumping does it turn itself up onto one of the cups and then jump, or does it jump from a side position?
It would be like
No,
like
it
on
jumps.
the
It jumps from side position.
it jumps from the
Yeah,
side.
it jumps from side. So it's just gonna it compresses like this, and then it's gonna release, and that's what allows it to jump. So it can really be any position.
Okay.
No, that's for the.
Now, and then you were talking about using some piezoelectric. How much power do you think you're going to get out of piezoelectric kind of things?
So I haven't we haven't gotten too deep into piezoelectric yet. So I'm not sure exactly the exact energy output, but even if we can get a little bit, then that would take a bit of burden off of the solar panels. So I thought that could help out.
We
Okay.
didn't look too deep into the piezoelectric stuff because of cost, and we didn't want to spend a ton of money on
Yeah, but
materials.
that is very costly. So
Well, and I I don't think that we look into it some more. I could be wrong, but I think that you're looking at some there's not a lot of power gotten from piezoelectric in terms of consider like I have a clock at home and it has a little piece of it's a piezoelectric and they for 1 point using a double A battery it will make it vibrate enough that it can move the second hand, kind of move the workings of the clock. So it's not a lot of power or vibration, but you should certainly look into it some more. Does that make sense?
yeah.
Okay. Um, and so now in terms of those wires, you guys don't get to determine what kind of wires those are?
Yeah, that's not really our job unless I mean if we come up with like if we find that piezoelectric is good enough to implement and can be maybe like layered on top of the material that the body team uses, yeah, then maybe that could work. But that's mostly the body team's idea and the jumping mechanism sub team.
And that sounds great. Flo, you got any thoughts for him?
Yes, so on your hold up your little model again. And instead of punching holes on one of the end, if you could add a ring with holes, because one of the other things that students should start thinking about is being able to fix the robot if it breaks, right? So
Yeah.
if you had something that you could take off and fix the little wires, that would make it easier to be able to fix if something breaks or you have to replace some wire or something like that. So you could make, and if you do 3D print it, try to 3D print it in a different color so we can see, hey, there's a ring with holes around it that is going in, because you got to be flexible enough to change things as your other teams change things too. So that, but I like the idea of piezoelectric. I think I have a bicycle that has a motor in the back, and I can put it in exercise mode, and it's run on a battery and a computer. And in exercise mode, because I'm pedaling, it generates electricity for it.
It's really cool.
Not very much, however. But cool. All right. So thank you for working on this, and thank you for working with the other groups. You're off to a really good start. I appreciate that work on that.
Thank you.
Excellent job, team. Keep this up.
Yeah, really good. So the next team, and you both have a wonderful afternoon.
Thank you, sir. Oh.
So they're staying on Emma's computer, it looks like. Okay, good. You're muted. There you go.
Hello.
Hi.
One second. We're just trying to share this new screen.
I like the tarmac in the back.
We haven't used that yet.
It's fun.
Yeah. Yeah.
Yeah.
There's Noel.
Hi, Flo. I'm bouncing between these and then the comp sci ones are going on simultaneously. So I'm like
Awesome.
hopping back and forth.
It's good to see you.
Good to see you.
What? Let's escape. Is it
Escaping on there.
Huh?
Oh, here we go.
Got it. We almost got it. I don't think it's anything.
I'm confused how they have this.
This is very frustrating. There you go. Okay. Can you guys see the screen?
Not yet.
Okay. No, we're just putting it up right now. Yeah, yep. We're putting it up right now. Yeah.
All right,
Yeah,
we're
okay.
sharing the screen right now, and this one. All right,
Yes.
now you got to see it.
Yes, we
All
do.
right, perfect.
Thank you.
Okay. Sorry.
All right, yeah. So we're presenting lunar jumping robots. We're the robot body team. My name's Eva.
My name's Joey. Just click.
All right,
Yeah.
so to begin, so for our problem, we've been prompted with the same like problem as everyone, that we need to make a robot to like be able to take pictures and images so that we could have so we could be applied for like research. But the problem is that there's like a lot of rocky terrain on the moon, and it's very difficult for robots to like move efficiently and move over big craters like up to the size of a baseball or even bigger than that. So the solution is to have a jumping robot rather than a robot that like is able to like move around on the surface. So that's what we're trying to figure out is the most efficient way to make this robot jump.
Yeah, and if I just could add, specifically in the division process of specialization with this project, we're specifically working on the actual jumping part of the robot, like the legs per se, and the actual encasement of all the components, electrical components.
So for our criteria and constraints, so like I said before, the ground is very hilly, so we're trying to make it jump rather than that. And another really important aspect of this project is that it's not always about the height, and the minimum we realized was 3 feet for it to jump, and it's a maximum of 10 feet, but our goal isn't to make it jump 10 feet. Our goal is to make it be able to take the most efficient and like most perfect pictures that we could possibly take. So we haven't necessarily found that ideal yet. We're still kind of more focused on that, but that it's going to be definitely something that like we're going to consider and have to alter our design later on once we figure that out. And then another important thing is that we want to just be able to put the robot on the surface of the moon and then let it take as many pictures and let it reposition itself and go into different parts of the moon to take as many pictures as possible without any interference of like the astronauts. We're trying to be as mindful as we can about the mass of this whole thing and the size of it. Like we remember when you came into our class, we talked about it's really important to have it as small as possible and as light as possible. So we've been really trying to make it compact we've been using carbon fiber for the material to have it super light. But we're still working on it, of course. And yeah, so the robot's not going to be driving, it's just jumping. Yeah, so similar, these are some more constraints. I kind of like went over this, so I'm just gonna move on.
Yeah. You don't have to go through it again.
So as we started this project, we tried to like research a bunch of different robots that have been previously been used like for jumping, not necessarily for this exact type of project, but just the mechanisms. And the one that we kind of took on was Tumro, and this robot kind of took our attention because we were really able to kind of visualize it for our project by it being kind of compact, having very limited material so that it would be light. And we also saw like in the middle of the robot, we thought that we could kind of implement some encasement to have the rest of the materials. So although it's not necessarily on this robot, we kind of are trying to mimic this for our own design. Other solutions, the other like robots that we saw, there was one that was like a slingshot, but we realized that that wouldn't like really work for us because it would be very difficult to attach different components to that. So this is the design that we decided to stick with, and then we'll like move on to sheets, so see how we did it.
Yeah. So this is kind of the first initial sketch we made. It's pretty similar to Tumor in the sense that it's got the legs and then the motor to wind it up. So I hope you appreciate my great drawing, but the black is the legs, the blue is the actual container. We haven't really gotten to that part in the sense that we've been working on the legs more like specializing in the legs for now. But we're kind of waiting on everyone else to see what components they need, like the coding team, like what kind of board they need. I think they're reusing a Raspberry Pi and any other wires or components for them. We're also waiting to see what kind of solar panels the solar panel team ends up choosing. And then in orange is the motor. We also have to secure that, but again, we're waiting to see what everyone else is working on. So it's kind of in the developmental stages right now still. But we are, for the most part, sticking with this design right now. But we've been, as I've said, we're focusing on the legs, and I have a couple prototypes to show you guys. Yeah, so good segue. Here, yeah, so this is the first kind of initial prototype we made. If you can see, it's just kind of like a rectangle with circles, or sorry, holes at the top and bottom. That was kind of mainly for testing purposes. But the problem with this one is the compression's good, but attachment to the robot is hard. So if you can imagine, like, let's say the hexagonal base that you see on the screen right now, just imagine trying to secure this to the side of that and like have it compress. It doesn't really make sense because if you'd be screwing it on from here. So Eva had the idea to kind of put the connection points at 90 degrees, like parallel to each other. But the problem with this one is when you compress it, the ends start to go in towards each other. So if you have this secured and it's pushing down, the compression doesn't really work. In regards to the hexagonal base, we think we're going to do that for the most part, just because we want to kind of get as many of these on there as we can. So we're thinking 6 to 8. So maybe we'll go with an octagon, but definitely at least 6, because we do need to get this 3 feet off the ground, keeping in mind the weight of all the other components. There's a click. Yeah,
Yes.
got it. So here is a little video of us testing. It's like 3 seconds, but yeah, so pretty cool. Basically, I printed this little box to test in. It's like hollow on the inside and it's got a hole on the bottom. So what I did was we fed a string through these 2 holes, and then this went inside of the base. And basically, we were pulling down. We would put this over the side of the table and pull the string down, and this would kind of compress, and then it would just we'd let go, and it would just go up. For our purpose, it was pretty good. We haven't really gotten into like the die-hard like testing with measurements and everything. We're kind of just seeing if the filament would work. And it was actually on my bad. I printed this with regular print instead of carbon fiber filament. So, but we did see that it worked anyway. So,
And to add,
sorry.
to add, we knew that this design wasn't going to be our final design, of course, but the reason that we like had to start with this is because we didn't really know what dimensions we needed our legs to be. We also didn't like, we were also kind of trying to play around with the thickness of the legs to figure out which one would be like durable but yet flexible. So that was the reason that we have like, you see the bunch of different thicknesses of the like legs here.
So that brings us to our most recent design. So I was really big on Legos as a kid, and I was kind of thinking about, how can we attach this to the robot, but also not limit the compression. So I don't know if you guys are familiar with Legos, but basically if you're looking at the one on the left, the Lego picture on the left, that's a clip, and then on the right is a bar. So basically those two kind of conjoin together, and it's like a hinge. So I kind of had the idea to take the clip, turn it into like an axle. So this is our design. Basically, there's a dowel in here. Sorry, there's a dowel right here. And then right here is 2 legs. And then these connection points on the outside are small enough. They're the same thickness as the dowel, or maybe like 0.1 millimeter bigger. So like if I pull on this or push the pin, it doesn't move. But these legs on the inside, and you can imagine that this would be like one piece connected to the base. It has free range of motion. So it's like they're moving freely. So what this does is you can secure these to the base, and it allows for full compression without the need to secure it at the end of the leg. So we've kind of solved the issue of where to attach the base, and also why, like, are we limiting our compression? So we have full compression and we can secure it to the base. The only thing we're thinking about now is how many legs do we need? So if you see here, there are 2 legs, and that was a print error, so that wasn't intentional. But we've kind of taken that idea into consideration because if you look when it compresses, it kind of bows out a little bit. So I was talking to a teacher here, and he kind of brought up the fact that, maybe it's good that they bow out a little bit, because if you have one solid piece, that's very strenuous on the leg. So if you have a bunch of little ones, then you're allowing the legs to take the shape of what they want more so than restricting it, and it would probably cause less breakage. God forbid something happens on the moon or anything in testing. So we're kind of embodying this idea of small legs, but more of them. So if we do something like this, we'll end up probably having like 12 to 24 little legs, which we're hoping is enough to get at least 3 feet off the ground. And I'm pretty sure that brings us to, I'm gonna pass it back off to Eva, and she's gonna talk about some other possibilities.
So after we before we were able to look at this prototype and realize that this might be a possibility, we started thinking about different things. And we came across this video from Mr. Beast. He created these arms, and it got us thinking, how can we kind of maybe implement this to our design? And so we came up to this sketch at the bottom of kind of making it look like a spider, and then this would kind of solve our issue because we're still kind of unsure how we're going to encapsulate everything using this design. So this design would allow us to really encapsulate everything, and then have the legs and have CO2 cartridges on the legs that will be able to accelerate the robot upwards through the collision with the moon. The only problem that we foresee with this is besides actually making it work, is the moon dust. And with each collision, the moon dust will likely definitely kind of become even more, it'll be maximized. So that'll be something that we will have to consider, but a solution to that would possibly be making camera lens open and close, and then open at the maximum height to take an image, and then close again before coming back to the moon and between that time. So we're just unsure in what direction we're going to go. We're going to kind of keep going with this idea for now. But this is definitely a solution that we're willing to consider after.
And the trade-off between the two, with CO2 cartridges, with this robot, it's definitely going to give it a lot more oomph and get it off the floor, for sure, more. But the thing we're thinking about is reusability. With CO2 cartridges, you'd have to replace them every time, so you'd have to bring more CO2 cartridges if you want to take more pictures, which adds weight onto the ship, as opposed to one robot where the legs it's reusable indefinitely for the most part. But the thing we're having a problem with this one is not only we're unsure yet if it's going to get off the floor, but if you look, it is starting to bend a little bit, because the filament we're using has high material, not high, but it has some material memory. So if we bend it, it kind of retains the bent shape a little bit. So we're thinking maybe replaceable legs, but 3D printed legs would be a lot lighter than CO2 cartridges. But that's just something to think about for us and you guys as well, if you have any suggestions.
Yeah, so that brings us to our questions what material do you guys suggest making these legs out of? Because we kind of came across to the conclusion to use carbon fiber, as it's light and flexible, but we're open to definitely trying different things and different materials.
Okay. I like some of these ideas. I think you guys are working on some really cool thoughts here. In terms of the legs, the idea of using carbon fiber does sound very appealing to me. They're not without difficulty, just because you can imagine when you're working at the temperature range of what we see on the moon, that could be a problem, right? And so, at what point do we start saying, well, we need, like steel or aluminum or something like that? And so those are things that we can worry about later. First, I want you to worry about how are we going to make it jump, and how's this body going to work, or whatever. And so now the other thing, you had mentioned using the CO2 to be able to kind of push it off. I'm not opposed to that. However, you might want to see about you don't want to be using CO2 canisters over and over, because then you have to always supply with a bunch of canisters. Now, you can make air cylinders that don't don't release the air. So they throw it out and then you just compress that carbon dioxide again and you throw it out and then you compress it again. And so there are some systems that do that if you want to continue with the idea of using the carbon dioxide. Okay.
Okay. Yeah, sure.
that's
So those are things to think about as well. I like some of these ideas. I think they're awfully cool. Now, do you have anything can you stop sharing and show me what you've got on the table there?
Like with this?
Is that the only thing you have right there?
In terms of like testing?
Yeah, I didn't know what kind of other equipment that you'd printed or tried out.
Oh yeah, so this is as far as we've gotten with like test like this is our most recent prototype. I literally printed it I think yesterday. But like I could show you the previous prototype if you want to see like one of those jumps like in the video.
Yeah, you showed us. That's actually really cool. Go ahead and show us that too.
Sure. I will I have to go get a string. You can move on to the next question if you want. I'll be right back.
Yeah, so
Okay,
another thing that we're considering with all of this is, especially with the hinges on this like prototype and considering the moon dust, do you guys foresee any issues with like say moon dust getting stuck in these hinges and not being able to then function later? Or do you think that will be like kind of clear of that?
I think that you want to make sure that you have enough space so that the pin for the hinge can release any of that dust. I don't think it's a stopper for anything. So I think you've got an interesting idea there. Okay?
Okay, that
Good
sounds
job.
good. Yeah.
Oh, okay. So you're ready to demonstrate?
Yeah, sure. So basically what I was saying, we'd feed a string through. It has a knot on the end, so it doesn't go through on one end. Feed it through the bottom. It's a little finicky, but it's just for testing purposes. And then I don't know if you can see in there, but basically pull the string down and it compresses. And then how am I going to show this? You want to just put your hand up. Just like on the bottom. Yeah, sure.
Oh, okay.
So then, right, so Eva's hand is acting as a table. Pull the string down and it goes up.
Okay.
And that kind of simulates the compression. It's getting to about this point, which is kind of where we want it. And then just seeing if it gets up. Granted, this is with no weight, and it's fairly small. So we're probably thinking that the legs are gonna be, I don't know.
That's an issue we're running into is like trying to figure out how big we need the legs to be so that there's still ample space for it to compress while also keeping the materials from the other sub teams like encapsulated inside.
Right. Okay. No, there's a lot to think about in this. So, and you were showing how you had made a mistake where you had printed 2 instead of 1.
Yeah. So this was originally, so the print was so you see how there's 2 here? These are supposed to be 2 separate legs. So this was supposed to be one piece. If you can imagine, this was supposed to be one piece, and then these were supposed to go in the middle. The dowel was going to go through, but for some reason the print just I tried it like 3 times and it just wouldn't work. So, but they got halfway through. So I was like, you know what? I said to my teacher, Mr. Lefter, like, just give me, I'll try and see if I can make it work.
Sure.
Yeah. So I tested it out. What I was really focused on was the hinge part, allowing for the compression. But then I was talking to the automotive engineering teacher and I was like, oh, there was a print fail. And he's like, actually, I think I like that more than one single leg, because he's right. When these are compressing down, they kind of want to go out a little bit. And allowing them to compress however they want takes the strain off of them. So these are pretty lax in the middle as opposed to diverging in different ways, which ultimately will benefit the robot by having it be more reusable and not having to have legs replaced so often.
Yeah, I totally agree with that, because I've had a team that their legs kept snapping. They were compressing it and it kept snapping. This takes off the pressure. That was a great mistake. And I love that you're using the Lego knowledge that you have. That's why we hire you, because you've had different experience than our usual NASA engineers. I mean, Legos was real important in your play.
That's right.
All those Christmas gifts my parents got me finally got put to use.
That were really expensive too. So.
Yeah.
No, I think that using Legos as part of your prototype is a great idea.
Yeah.
And there are times where you're going to say, well, it's too flexible now for whatever, and you'll move on to another part. But I think that utilizing all these different things is really valuable. All right, excellent. Where do you guys want to go next now?
So, with this prototype, I'm going to try it now to get a successful print, which shouldn't be hard because, if these are what we're looking for, then that should be fine. And I'm going to try to print now, probably anywhere from 12 to 18 to 24. And then set up a new base so these little flaps are kind of just stand-ins for like the actual attachment on the base. So imagine this being like one actual piece with a hole in it and then the dowel going through. So my next goal is to make like a top and bottom base and like get a full test, like just have a full test robot just to see if it'll jump.
I think that's a great idea. I think getting a jump is really critical.
Yeah.
And just finding out if your plan is feasible, and then you can start making it better as you see. Good job, team.
Thank you so much. This is awesome.
Thank you so much. You have a great afternoon.
Thank you, Dr. Dole. It's nice to see you again, by the way.
Yeah, you too. Great job.
All right, we're gonna pass it off to Ilias and Alejandro. They're gonna talk about potential energy storage. But thank you guys so much. We really appreciate your help.
Thank you so much.
Thank you. Great
Bye, guys.
presentation. Have a good
Thank you.
afternoon.
You too.
Thanks. Yes, thank you for helping them, Eva.
All right, you guys can hear us, right?
Yes, and see the PowerPoint, storing potential energy.
All right, good afternoon. So we are the storing potential energy subgroup for this NASA HUNCH jumping robot project. So yeah, this is how our presentation is split. We define the problem that we were given, the research, the brainstorming, the prototyping, and our ideas. So the problem we recognize. Okay. So okay. Oh, sorry. Yeah. So NASA needs us to create a robot that can jump 10 feet high on uneven and hazardous surfaces on Mars. And they want us to jump up 10 feet with a camera to collect data. And so our subgroup, our task is to figure out how we're going to make the robot jump, specifically what springs we're going to use for the robot. Right now we are, and we'll talk about this later, we're working with motors, gears, and a gearbox that's going to contract the prototype, which ideally makes a jump. So research, we went in brainstorming. So actually, yeah, sorry. Okay, is there a way to actually speaker notes on this? Okay, so we went through multiple gear types. If I could pull up speaker notes, it'd be helpful because there were 4 gear types. I don't have them off the top of my head right now. The 4 spring types. Oh, sorry, I meant spring types. And the moon environment. I did have one question on that, but right now my understanding is that the only thing we're accounting for is the different atmosphere because the different gravity. But I just wanted to know if there was anything else we should be considering. But we can answer that question later. And then brainstorming.
So for the brainstorming part, we we worked as like a full team to figure out like to get like started because if we went sub team by sub team, we felt like we weren't gonna like be fully prepared and connected well. So we wanted to make sure that we all had an understanding of what our jobs were. So the the main like robot that we looked at that we really like found interesting was the tumor one, which is the one in the top right corner. Um, so that's like how we came up with like this is like the type of idea we want, where we have like the legs be like the main part of the body, and that is what leads to the robot jumping. And then we also have a latch mechanism that was used in the tumor. So this was one part where we are still currently struggling a little bit, but we have a separate idea that doesn't use like the latch mechanism as we're seeing it might be a little bit difficult with like because our body isn't going to actually be that big. So that's something that we're looking into. So then we started developing prototypes, and this was our first drawing. Like, no, not our first, like one of our final drawings of like our final idea. So what we were in charge of was since we're gonna get the energy to make the robot jump from the legs that the last group talked about, we needed to find a way to compress those legs in order to try to get enough energy for the robot to get off the floor and jump. So our first idea was just using a like a spool and a DC motor. But while doing this, we came into a few problems. One of them being, as you can see in this picture, like the string. This is a bad picture, but like the string, it wasn't gonna like properly spool it and compress the robot, as well as it couldn't like lift too much weight or like compress too much weight as we when we tested it. So in order to try to fix this problem, we decided to go with a gearbox and we 3D printed it. So we had the box, some gears, and because one major problem we faced during this was we didn't have any like shafts that were like that would be able to like hold the gears. So we 3D printed our own shafts. And that was a little bit difficult because since we're trying to keep this robot as like small as possible, we had to make the shafts small as well, so they would constantly break. But after a while, we decided to just try to make the holes of the gears a little bit bigger. Therefore, the shafts were a little bit more sturdy and they wouldn't fall apart and break. So that brings us to our prototype, which is this right here, where we made it. I actually have it with me right now. Um, so this is like what it's looking like right now. I don't know if you can see where we added like the thing for the spool in order to be able to like to keep the string in place so that we could like actually like compress the robot. And while testing this one, we were able for it to be able to compress a lot more weight and like actually like work instead of like the other spool where it would just like stop working. So now that we have this and we know that we could compress the robot, our only problem is holding the string and releasing the string to be able to make the robot jump. That's what this slide is about because not only do we need to like hold it and release it one time, we need to do it multiple times to try to get multiple images. So one idea that I have is using an H bridge that we would use an Arduino and connect to an Arduino. This way it would be easier to control we would be able to control the motor, the speed of the motor, and the direction of the motor. We still haven't tested this out and we're not really sure if it will work, but this was like our final idea that we were working on lately. And that's it. Thank you.
Okay. One, I really like your gearbox. It looks like it might be a little bit bigger than it needs, but I'm not sure what else you're planning to add to it. Um, can you stop sharing and show us that?
Sure.
I should right here. It's okay.
There you go.
All right,
Okay.
so this is what we have right now.
Yeah. And how well does that work?
So it's able to like actually compress. It does like actually work. Once in a while, it does like come apart like inside the box because we don't have like the correct shafts. But if we are gonna go with this, we would try to find the the best possible fit so that it does truly work.
Very good. And I think that you got a really cool box there. Now, the hard part is so you want to reel it in and then you have to release it so that it releases quickly without also turning into a big wire nest, right? Okay.
Yeah, that's our main challenge right now.
And so, um, if do either of you fish?
Yeah, I did a little bit.
You do a little bit? Okay. So when you've got your reel, you're cranking it in, right? And then you flip the baler bar and you cast it, right? That's exactly what you're trying to do here. Does that make sense? And so I'm suggesting you might you might see if there's videos of how the reel works for a fishing rod. That might help you. Now, I understand that there's two different ways that these work, right? There's the one with the baler bar, like what I'm talking about, but there's also the other kind where it reels in a different fashion. Check both of them out, and there might be some value to how you guys are going to do it. Does that make sense?
Yeah.
I like what you're doing. That's really cool. Okay. Now, do you guys have to know anything about or are you guys the ones that determine the size of the springs that you're going to reel in?
So the body is the one that's focusing on the legs, and that's mainly what's gonna decide how big the robot is gonna be.
Okay. And so to help you out, it might be good for you to go out to the hardware store and start looking at some of the different springs that they might be looking at. And you might even go with that team, right? Say, hey, let's go meet at Ace Hardware Store. And then when you go in the store, you can go find ask them and they'll say, hey, I'm trying to do springs, and they'll take you over to this bin that has 20 different drawers, and each drawer has 20 different springs in it, and you can sit there and play with it and decide which one, this one's too strong and this one's too weak. Does that make sense?
Yeah.
So I like where you guys are going with this. And then in terms of okay, so you're talking about the pins and the screws and whatever for your box. By shrinking down your box, you might also be able to eliminate some of your pin problems as well. Just because as it comes closer together, you get a little bit less wiggle and that kind of thing. Does that make sense?
Yeah. Yeah.
I think you guys are going along really well with this. Excellent job, team.
So what about your wire that you're reeling on to your spool there? Is that just a metal wire?
Right now, it's just a really thin wire. This isn't the wire that we will be using. This was more just to test. So for the actual design of the robot, we're gonna have as I don't know if the previous team mentioned, we're gonna have multiple legs, right? And we're gonna try to connect all those legs to one end of a string, and then that'll be the string that we will be pulling.
So Glenn always suggests maybe some, what do you call it, stranded fishing line?
Yeah,
that might reel in better than wire.
Yeah.
And part of it is you don't want it to stretch. And fishing line will stretch, but if you have the stranded fishing line, it doesn't stretch the same way. Is that okay?
And it could reel in a lot better than that wire does. So visit a store that has fishing supplies. I'm sure you have something out there.
Sure. Excellent. Do you have any other thoughts or questions, guys?
I did have one question. It's kind of a general question. I'm assuming that you've seen other examples, or or I'm assuming that the jumping robot has that this competition has happened before, and you've done it before, right?
No, I've never done this before. This is pretty exciting for the way we're doing.
Okay. All right, no problem. My question is do you think that the gearbox is a good idea? Do you think there's a better idea that could possibly work better? Yeah, so
Gearboxes are a great idea. The fact that you guys are making your own is interesting. It's not necessary, but if you guys are on that path and you like it, you can. If you go to what's it called? Spark Fun and look up geared motors, you can find a couple of different geared motors, and you can either look at, is that what you're looking for, or you can specialize with what you're doing, but it may give you some good ideas for it. Okay?
Okay. Got it.
Yeah.
Now, there was another question in your presentation. What was that question?
Like, should there be any other considerations about the Mars atmosphere besides gravity?
Oh, okay. Well, and remember, we're trying to do this for the moon.
Moon.
And there's
Oh,
a
yeah,
little
the moon, sorry.
So on Mars, there's air. On Earth, there's some air. There's a lot more air. But on the moon, there's virtually no air. And so that means that when it's launching and when it's falling or whatever, it's not going to have the same kind of effects as what we might have here on Earth. And so there's lack of air, there's lower gravity, very fine powdered dust are probably the three main things for you to consider. Does that make sense? Okay. Good questions.
And keep
Oh,
keep working with the other teams. Your success depends on your communication between your teams. I love that you have all these teams working on it, but success comes from great communication and asking questions.
Very good.
Yeah. Awesome.
Other gentlemen?
All right. Thank you.
Thank you so much.
Get the other
You have a
team.
great afternoon there. This is the last team coming up, right?
Yeah.
So have you been listening to all of the reviews? Have you been able to listen to all the reviews or just yours? Okay, well, don't worry about it. I'm putting it online so you can watch the recording. Okay, bye-bye. Hello. So you're muted. Oh, there you go. And I wasn't sure if I could see anything but your heads, but you're great. But you're muted. You're muted still. There you go. Yes. Introduce
Good
yourself.
afternoon. My name is Aiden Charles,
And then my name is Grace Otavera.
and we're part of the control sub team for the jumping robot.
This should be a bit better.
And we see your PowerPoint.
Wait, this is the wrong. Hold on.
Maybe if you click space, it'll be.
There's no. That's the screen that
They can see the screen.
Yeah.
Yeah, we
Why
see
did
it. We see control sub team.
What are you trying to open?
No, I'm trying to make this screen bigger.
Oh, that's fine.
That's fine?
We're fine.
Yeah. All right.
Okay, so as we said, my name is Aiden, and this is Grace, and we're part of the control sub team for the jumping robot project.
Awesome.
So first, a quick overview of our presentation. We're going to be going over the objective. I believe some of the other teams already did this, but it's the same objective. We have some constraints that we needed to address, as long as the research process which we took when we were thinking about different ideas. We had a decision matrix for the microcomputer, different ideas as to what type of microcomputer might be best to use for this project. Components, we have a list of the components that we thought about and the list that we are almost sort of finalizing on using. And then we have the workflow, which is basically just the key stages showing the planning and the testing process of how the robot should hypothetically function. So a quick overview again, I think the other teams covered this, but NASA just needs a way for the robot to travel efficiently across these uneven surfaces or these planetary bodies. And our goal is to make it so that the camera is able to take pictures, images when it's at a certain altitude and send these images back via Bluetooth Wi-Fi.
So then we have the constraints for our sub-team. So the first constraint is to capture images on ascent and descent. Then the camera needs to capture ground images from height. Then the camera produces good quality images. It needs to maintain camera orientation during jumps. It needs to transmit images to phone or rover reliably. It needs to store images briefly and then transmit it in batches. And then optional flashing lights for easier location. And then when Dr. Gold came and visited us, she brought up the point of moon dust, and we've been talking to the body team of how we're gonna coordinate that. And then for our research topics, the first one was the camera. And for the camera, we were responsible for how it's going to trigger to take photos. And we were either going to do it at altitude or through a time sensor. So we were going to use either an altimeter or a timer. And then this was good for either at a specific altitude or immediately after takeoff. And then this lets the robot collect a visual data during the jump or a height estimation. And then for the operating system, we chose the Raspberry Pi OS because it lets us use Python. And then for the motor, to operate the motor, we needed to program it to rotate in both directions, winding the string to build tension and unwinding it to release the tension and launch the robot upward. Our research focused on understanding how the motor's movement controls the string system and how code can precisely manage speed, direction, and timing to make the jump consistent and repeatable. And then we were talking with the energy storage team, and they decided on using a 9 to 18 volt motor. And yeah, we were talking with them. And then lastly, the display we chose was, we decided to go with a display that could connect to the mini HDMI adapter for Raspberry Pi Zero, but we didn't have one available. So we went with one that could connect to the Raspberry Pi V1.2, which you'll see in the next image. Or the next image. This was the decision matrix for the microcomputer. So we broke it down into different categories and criterias, and then we weighted each criteria based on what we had available. And based off all the scores, the best one was the Raspberry Pi 3.
So here's an image of our display as well as the Raspberry Pi on the back, along with the connected camera. I have it also physically here, but essentially I just wanted to show that this is the display we ended up using. It's Raspberry Pi's own display, so it worked paired nicely with the Raspberry Pi V1.2B, and it allowed us to also connect the camera and have a visual display of our code. That way we could write code on the same device as we're viewing the code. As Grace said before, the previous issue with using something like the Raspberry Pi Zero was that it needed a mini HDMI adapter in order to connect it to a bigger screen or monitor, and we didn't have that at the time, so we decided to use this for the time being. And I believe we're going to stick with this now because it also does have Wi-Fi and Bluetooth capabilities. It's the same thing, but here's the physical thing. It's not connected to power right now, but here you can see the camera with the ribbon cable. And then this is the Raspberry Pi along with the display Raspberry Pi connected to the back. And then this is the display screen. We also have this was a prototype we made for the camera to hold the camera. So essentially it's just a 3D printed box with a hole at the bottom for the camera. It also has a hole on the side for the ribbon cable because we needed something to hold the camera, keep it steady. And we have 2 holes here on the sides. Our goal was to try to do something that could keep the camera in a downward facing orientation, which is what we were going to ask you guys about, because that's really our biggest priority right now, along with moon dust. But this is just our first prototype of the camera holder.
Sounds good. And so how do you think you want to orient the camera?
So it definitely needs to be facing down constantly. That's what our goal is because it'll be at the bottom of the robot facing the ground.
Okay.
Our main thing is just keeping the robot, because the robot's obviously going to be jumping, so keeping the camera pointed down, that's what our main concern is.
And I think that sounds pretty good. So do you plan to make like some kind of a camera holder at the bottom that holds your bracket as well?
Yeah, something needs to hold the camera, something needs to hold the Raspberry Pi itself. But yeah, that should all be mounted at the bottom.
I think that's great. You're on a good path.
Mhm. And I thought somebody else mentioned that the camera would be in the container that would open when it's up high so the dust wouldn't be affecting it so much.
That part as well, yeah.
That's awesome.
Thank you. It looks like. Okay, so here's what I was talking about before, the mapping out of our steps. We have to prepare, the robot has to prepare to jump. So whatever that may be, I believe the body team is doing some sort of mechanism where the strings would be pulling in order to create tension. Yeah, in order to create tension. So the robot would perform the jump and then it would take the pictures while it's in the air. So after it takes these pictures in the air, it needs to land. It needs to send these pictures to a phone, which is in the requirements. It said via Wi-Fi or Bluetooth. We have both on the Raspberry Pi that we're using, but we haven't decided which would be best yet. It needs to reorientate itself, meaning maybe it landed on its side or maybe it's not standing upright. It needs to make sure it's standing upright, and then it needs to repeat the entire process, recharge.
Does the Raspberry Pi have a spot for a mini SD card also?
Yes, it does.
That would be a good place to save the pictures also, just in case the astronauts aren't connected to the
yeah.
to the
And then same thing, tracing steps for the code. So we need to initiate the code. We have to wait for a launch signal. We're thinking we could do something like an LED light attached to the robot. And then this will wind the motor, the string, and begin the preparing for jump process. When it releases the string, the robot should hypothetically jump into the air. It should take some pictures, and then it stops taking pictures. Once it lands, it resets the robot, and the code repeats.
And then after we traced all the steps, we made a component list just so we had all of our items listed out and we didn't have to wait for anything. And then it was the Raspberry Pi Zero, Raspberry Pi V1.2B, the Raspberry Pi camera module V2.1, the Bluetooth dongle maybe, but then we found out that the Raspberry Pi that we decided to use has the Bluetooth already built in, so we don't need that anymore. And then the motor, which was the 9 to 18 volt, the buttons and switches, the LEDs to signal, and then the micro SD cards. And then these are our resources. And then thank you. Any questions? And there are emails if you have any more questions.
Excellent. No, I think you guys have it planned out well. Now, how much of that do you expect? Do you have to do all that coding, or do you have access to code for that?
We were planning on using whatever resources were available to us to like sort of make the coding process easier. We haven't began coding yet, but we started things like taking pictures on the camera, making sure. I wish we should have gotten the picture, but we took some pictures on the Raspberry Pi, tested out videos on the Raspberry Pi as a possible option. And that's as much as we've done coding wise so far.
Okay. And so some of that is already available on if you go to SparkFun and you go to the Raspberry Pi that you have, I think you said a 3, is that correct?
The Raspberry Pi V1.2B.
Okay. And so if you go to the Raspberry Pi and you go to that camera, you can probably either find or download the coding to be able to run that kind of thing, and and they might have some pointers for you as well. So SparkFun, they already have a lot of that code available. Does that make sense?
SparkFun, you said?
SparkFun.
Okay.
Okay. Look up that same one and they'll have some of that code. Now, because you want it to do some specific things in a specific order, you'll have to write some of that code. But I think that some of it is already available for you and it'll help out. Okay?
Okay. Thank you.
And so then now have you already found the other team was looking at what kind of motor, is that right? And so you might want to coordinate with them. They might be able to have, if they're choosing one particular kind of motor, they might want to coordinate with you ahead of time to make sure that you're getting a motor that has the kind of controls that you need. Is that okay?
Yeah, we were working with them previously because of things like power.
Something's happened. I can't quite hear you. Say that again.
Can you hear me?
It's muffled. I'm not sure why. Hold on.
Yeah, no, it's muffled here too. You were
Okay.
coming in loud and clear, Aiden, and then it got muffled.
Okay. Go ahead and say it again. I'm turning up my computer.
Can you hear me now?
I can hear you. Go ahead.
Yeah.
Okay. Um, but yeah, we worked with the energy storage team who was working with the motor, and we discovered that the Raspberry Pi can't directly give the power to the motor. So we plan to use an external battery connected to the motor, along with the Raspberry Pi to run the motor itself.
Yeah.
Yes,
That
and
battery's
that
gonna
makes sense too.
Yeah.
Good job, team.
Yep.
Okay.
No, they can hear us. They can hear us. Yeah. Yeah.
Yeah, now it's actually a little bit better. I'm not sure what happened there. What do you think your next step is? What do you guys want to do?
Right now, we're just really waiting to see where everyone else is at in the project in our sub team. For example, things like the body team and the layout of their robot, how that's going to be working will decide specifically where our camera will be oriented. Oh, and again, we have to figure out a way to have our camera pointed down at all times. So that's
Yeah.
another thing.
That
And we
sounds
were
good.
trying to figure out a way to get all the connections to the operating system to the Raspberry Pi. Because we have to have them go to the battery and then back to the Raspberry Pi.
Yeah, and part of that wiring harness or however you want to do it is pretty critical. You can imagine that when it jumps, if you have your pins in one direction or a different direction, the jump could actually remove some of those control pins from their location. So keep that in mind as you're putting things together, okay?
Mhm. Okay.
I like where you're going with this. It looks really smart. Good job, team.
Thank you.
Yeah, I like how everybody has their role and communicate, communicate, communicate. That's the most important thing you can do right now because you're all on the right track. So thank you so much for
Thank you.
working all
Thank you.
this. And you can
Did you
always ask us questions whenever they come up. We're here.
Okay.
Okay. Thank you so much. Have a great afternoon there.
Good
And
job,
Have a good
team.
rest of
Keep it
your
up.
afternoon.
I think that's the last team for
Yeah.
Bergen Jumping
Yes.
Robot.
Thank you so much.
Oh, thank you
Thank
so
you.
much.
Thanks.
They're doing a great job.
Thank you. Thank you for giving them this chance, this opportunity to do something.
You bet. I
It's
think
all
it's good.
you.
We're lucky to have them. So thank
Thank
you
you.
so much.
Thank you. Bye.
Bye bye.
Bye.
Bye bye. Have a great afternoon. All right. Well,
Thank you.
Fairport High School is on. And
Hey, Flo.
hey, how you doing?
Good, how are you?
It's good to see you.
See you too.
Hey, Vince, good to see you.
We've got, hey, Glenn, how you doing?
I am great.
We got a lot of snow here for you.
Oh, good.
We have a lot of snow too.
So we only have half the team here because, flu cases are running rampant up here.
Oh, that's
my.
terrible.
Other two are out, but these guys are ready to pick up the slack.
Okay.
So
Excellent.
I'll let them pick it up. Go ahead, guys.
All right,
Awesome.
tell us about it, guys.
I'm Ben Blake, and I'm AJ Pegla. This is our robots. We'll show you a more in-depth picture later with that is labeled. So just yeah, it's got kind of a hexagon frame, and then we have springs going across here so that when we compress it, the energy is stored in these springs. And then we have motors up top that are going to turn some gears that move against this gear rack that will help it compress and release. And
Does
we'll
it jump?
Yeah, it jumps about a foot when we compress it with our hands right now.
That's exciting. Okay.
All right, we're going to move to our presentation now.
Excellent.
Okay, this is just our main slide. It shows our project, the people on it, everything to do with it. There's not much necessary here. And then here's our video. We'll see if it goes. Yeah. So for our design, we're using extension springs to store our power and I talked about it earlier. When we compress it, it's going to extend them across the legs. So for compressing the gear, we're going to turn, or compressing our robot, we're going to turn gears with our motors, and they move against the gear rack. And you can see right here, the gear has a little section cut out of it. And what that will do is when that section faces the gear rack, there'll be no teeth interlocking with the gear rack, and that'll allow all the energy stored in the spring to be released at once. And then for orientation and repeatability, we have arms on all four sides that when the robot compresses, they extend out. And so if it falls on its side, it'll kind of right itself. And then we're also making it bottom heavy to prevent it from landing on its side. And then for preventing dust, we put an irrigation hose around both of our extension springs, and that allows it to, the irrigation hoses are able to extend and they kind of cover the spring, which prevents dust from getting on them.
Okay.
And then this is a more in-depth diagram of our robot. So yeah, we have our gears and our motors on the tops. That turns against the compression spring. We labeled our arms, and then we have guide rails running along the gear rack to keep it oriented the same way as it compresses.
Our design stands out because it is very simple. It just turns the gears, moves down, and releases to jump. It's really easy. Not much can go wrong with it. It is very sturdy. It doesn't have much that can break outside reasonably. And it can reliably jump this around the same height if compressed fully.
Very good.
What we're going to work on next is controls. We're planning to use a Raspberry Pi 5, potentially hooked up to something else, a screen. Put some solar panels on it somewhere.
Yeah, we're considering that. Right now, we're just using batteries.
Yeah, not there yet. We only actually have 2 groups worth of people in total, and that was only a recent development. We initially only had energy storage. And then for our camera, we are intending to place it on the bottom of our robot.
Kind of on the foot.
On these legs. We're intending to put it on those, so when it jumps, it can take pictures pointing diagonally at the ground with different angles.
And then we're going to make the frame a lot lighter. Right now, the planks that we used are very wide, and it's not really necessary for our final prototype.
And it's a heavier wood. So if we make it lighter, it'll jump a lot higher.
Yeah, any questions?
Sure. Okay, go ahead and stop sharing, and then show me your prototype a little bit more. Can you bring it closer up to the camera a little bit?
Yeah.
Yeah, come around the table if you can.
Oh, here we go.
There you go. Okay, that's really exciting.
Yeah, we have the arms on all four sides, and then we have the gear rack going through the middle. Lower. Okay. Yeah.
Okay.
And then guardrails on each side, and then you can see the gears here. If I get a little closer, they have the cutout section, so they turn counterclockwise compared to the gear rack. And once they get back to this section here, it's going to all release its energy at once.
Very good. Okay.
Why don't you tell them where you got the gear rack?
Oh, I got it at USA Rollers and Chains. We tried ordering it, but when they learned about what project we were doing, they were happy to donate it to us.
It's awesome.
Yeah.
Okay. All right. And now I'm looking at your body sum, and it looks like you've got 1, 2, so you've got 6 hinges. Is that right?
Yeah, that's right.
Okay. Now that's a significant amount of weight as well. And you're using, looks like 1x4s or something like that. Is that right?
Yeah, something like that.
Yeah.
Something we were researching for the hinges were compliant mechanisms, and those are basically just one piece of a very light 3D printing filament that's meant to be very flexible and it will operate just like a hinge.
Okay. I'm okay with. Oh, go ahead.
It won't be as vulnerable to the lunar regolith because it won't be able to like get in the mechanisms.
Yeah, it won't grind against itself.
You know, that's actually a really good comment there. I wasn't thinking of that yet. Now you didn't use hinges on the other two legs.
Yeah,
They look like eye hooks. Is that right?
That's right. It's mostly about weight, and I was just trying to display another alternative to hinges if they didn't work. And the like stability of these two arms, they're meant to be lighter, so stability from side to side isn't quite as important.
No, and those are mostly just so that it'll stand up after it jumps. Is that correct?
That's correct, yes.
Okay. And so I bet you could go to just like a flexible plastic rod or something like that on the side. And that would avoid having those metal parts that are a little bit heavier. Does that make sense?
Yeah, and that would store energy too when it compresses.
No, I think that's great. You know, a goofy thought. What if it was a metal ruler or something like that?
Yeah, maybe.
Just a thought. I think you guys are on a really good path. I like what you're doing. Where do you want to put your now you said a Raspberry Pi 5, is that right?
Yes.
Where do you want to place that? Is that going to be on top? Is it going to be in the middle?
Hadn't thought about it much.
I think we want to mostly keep our weight on the bottom.
Yeah, so probably somewhere in the middle seems the most feasible because there we would protect it from anything and not add too much weight to the top.
Yeah, we probably don't want it on top because that's like more open to the surroundings.
Well, and having it inside the body is not a bad idea, just because it'd keep a rock from slamming into it or something like that potentially. And then the camera. Where did you want to place the camera?
Oh, let me show you. So we wanted to place the cameras on these here.
Okay.
On both sides, because that way when it jumps up, it'll be compressed. So it'll be like kind of like this probably. So the cameras will be pointing mostly at the ground on either side, and then it could snap two pictures of opposite landscapes every time it jumped, while keeping them pointed at the ground and not directly sitting on the dust.
Okay. No, I think that works. So you're thinking of having two separate cameras to be able to do that. I think that works all right. Is your Raspberry Pi able to handle two cameras?
We haven't tested it yet. None of us are experts on Raspberry Pis yet. We're planning to learn how to do it probably this week or next.
That sounds good.
Our group was originally focused on the energy storage, and we explored a little bit of the body, but we haven't dived too deep into the controls or camera yet.
Yeah, we're just trying to make it so it works the best we can with half the people required.
I think that's a terrific way to start it off. I mean, that is the most difficult part. Now, what kind of success have you had with the gears and the spot where there's no gears? Does that work okay?
We haven't tested that yet. I had to let glue dry overnight yesterday, so today would have been the first day we would have been able to test it.
Yeah.
Sounds good. How long does it take for it? In terms of your motor speed, how long does it take to compress?
Not too long. I'd say like around 10 seconds.
Uh-huh.
It's supposed to be a high torque motor, so it won't like compress incredibly fast, but it's not going to take like a minute or something crazy like that.
Sure. And just to put a point there, if there's reason to slow it down or anything, that's also not a bad idea. I mean, we want to be able to jump once every, 2 minutes or so would be perfectly fine. Does that make sense? And at some point that might give you more time for your solar panels to charge up kind of thing. Is that okay? Great job, guys. I like where you're going with this. The fact that you're getting a foot of jump out of that is really significant. I think that I think that you're going to be able to lighten that up and start getting a lot more jump than that. I think it's very impressive. Good job, team.
And I like how you're using that irrigation hose to keep you dust off your springs. It's light, it's flexible, it has all the great characteristics, and you won't have dust interfering with the. You're the first one that's covering the springs. You're not the first one that left that gear, the round gear with the space open. I saw that I think yesterday. One team was leaving the space open. So that's a really good idea, I thought, that you're doing. Do you have any questions for us?
No, I don't think so. Do you have any? I don't think so, no.
Okay, you can always ask questions, you know that. So
yeah, send us emails if you like. We'd be glad to help out. Okay.
All right.
Awesome. Well, thank you so
job,
much.
team. Keep it up.
Yep. All right.
Okay. Well, thank you guys.
No problem. Thank you. And let's see. Are you on again this week?
Yeah, Thursday I have one team going, and then Friday I have two teams going back to back.
Okay. Good.
Terrific.
Thank you.
Thanks a lot, Vince.
Say hi to Donna for me.
I will. Yeah, she had laughed.
Yeah.
Okay. I will. All right. Take care.
Bye bye. So we got the next team is in the state of Washington, and they're not due until a few 6 more minutes. So I'm gonna, and I don't see them on.
Okay, I'll take a break for just a minute here.
Yeah, me too. Thank you so much, Glenn.
We need to.
Sorry, guys. Go ahead.
Okay. Since NASA, we're trying to find the problem we're trying to solve. Since since NASA can't send a helicopter to fly on the moon and help with robotic missions, we need to make a jumping robot to send to take pictures. How we're gonna solve this problem? We find out what it's going to do and how it should work by following the steps provided. But the criteria making it jump, what we need to do is make sure it's able to take pictures on the way up and the way down. Constraints, the problems we might have is the jumping ability, because the control and the maneuvering on the surface will mess up the pictures if not done right. So the research, we're supposed to make it simple, make it light, and make it as compact. Don't overpower the jump, solar power or mechanical. Those are the two things that we're gonna use to figure out how we're gonna make it jump. I think the power, and we're supposed to make it jump without the dust particles and remove the dust off the camera. So, and make it remote triggered. How will the robot store and release energy to jump? How will you trigger the jump? How does the weight affect the jump? And what happens to the robot when it lands? So our idea is it's the same thing as brain research. So how we're gonna do that was just making it simple and everything that our research provided. So we're gonna develop the. Do I move this? Nope. Develop and propose among alternative solutions. Having less weight. The pros about it is having less weight depending on the robot, and it should, if it jumps 10 feet on Earth, it should jump 60 feet on the moon. it takes pictures of the moon surface and it's durable. HUNCH is gonna be small, has thin walls. Don't know how to make it survive the fall, and don't know how many jumps it can take before it's damaged. So this was our main idea. My friend Asa, he created an idea about a pen, how a spring would make it something jump. So we had a bunch of prototypes, but basically, our springs got taken, so we can't really show you, but it was supposed to be something like this thing right here. We're supposed to put the spring on the bottom of it, so like it could like compact and make it jump.
Okay, so wait a minute. Do you have a couple more slides left yet?
Yeah, I think we.
Okay, and I just didn't want you to keep going if you got more. I wanted to see what you had in your hand.
I think that might have been it.
Okay, well let's stop sharing and show me what you've got in your hand.
Sharing. Stop share.
Good.
Alrighty.
Okay, so what's in your hand? Show me that thingy again.
So it was like this thing. We're supposed to made a little screw bottoms. We're
Yeah.
gonna take the springs.
But that's some of the springs.
Yeah, but there was a different spring that was supposed to come to it, but it got missing.
Oh, okay.
For it to compact and make it jump.
Tell me about the spring you got there. What is that? Is that similar or is that different?
It's like different. It's like a lot more solid and like a lot harder to compress.
Compress? Yeah. Okay.
Yeah.
So how is the other one? Is it like a thinner wire or something, or what do you think?
It's like yeah, it's like a lot thinner, something like this, but it's like a lot rounder.
Oh,
It's
okay.
to, go around this whole circle.
Sure. Okay. Here, hold both of those up again for me. Let me see what you got.
We got these two.
Okay, so it's somewhere in between those two. Is that what it is?
Yeah.
Oh, okay. That makes sense. All right. Show me your white piece again.
It was this one, and we made a smaller one for
Now it looks like, are there threads inside there? Is that right?
Yeah, there's supposed to be.
Yeah.
threads.
What was your thinking for that?
We're supposed to like that bigger spring we had. It was supposed to twist and connect to it.
Okay. And that's pretty cool. What did you want to put on the bottom of that?
We're just trying to figure that out, but our first plan was to make these the legs, but so like the dust particles wouldn't barely catch onto the like a flat surface.
Sure.
And I was like, oh, that wouldn't work. So
Okay, so wait a minute. So the pointy side goes down into the dirt, is that right?
Yeah, that's what the plan was, but we couldn't make the body, so we just made this as a
That's okay.
making it jump.
And so you're gonna have 4 of those, one for each leg, is that right?
Yeah.
Okay.
We did like different sizes, so it's not like all even, so we're still trying to fix that right now.
Okay. And so you have these 4 legs. What was gonna be on top? How were you gonna do that?
We're supposed to create a body where the camera could go into it and take the picture. That's what the whole idea was about, but we weren't able to create that and brainstorm about that as much.
That's okay. All right. So you have 4 of these legs with feet like that, and each of the springs in there, and then you have a part on top, and that's where your camera's going to go.
Yeah.
Okay. And so, how were you planning to compress each of the springs in those legs?
So my whole idea for it to be like remote control was some remote how do I say it? It was supposed to be a mechanical chain to make it close out more. So that's
Okay.
what I was thinking.
So you were planning on a motor to be able
motor,
to
basically, yeah.
Sure. Okay. And then what? what do you think your next step is? Where do you guys want to go with your design?
Basically finishing off the project and like making all these legs even and trying to figure out what camera we're going to use to take the pictures.
Sure.
Then we're gonna test it out to see if it contracts more particles.
Okay. Have you decided what the top of that of your robot is going to look like?
We're probably gonna do go ahead, tell them that. Tell them about our base.
Our base was
Must be a rectangle or a square.
something like a rectangle or like a square or something like that.
Hold on. Okay. So this is just like, I mean, would something like this help out?
Yeah, something like that would help out. It would be depending on the camera, and I think that would
Sure. And part of what I'm trying to do is give you some options that are
Yeah.
close to what you're looking for. But I mean, just go over to the recycle bin and see if you can find some kind of a box and start modeling up your idea.
Okay.
And every time you put something extra on there, it just gets you that much closer to saying, that's what I want. And it helps you drive a little bit further. Does that make sense?
Yeah.
Okay. And so I don't know which way you'd put this, if you'd put it this way up or if you'd put it this way. How would you want to position your camera?
Because that hole on top, I would say it'd probably be facing down for the camera
Okay.
to have a cleaner picture. And so we would
Oh, okay. So wait a minute. What if I had the lid? I could unscrew it and I could put my legs on it. Does that make sense?
Oh yeah, that would make sense putting the legs onto the lid. So it could
Yeah. And that way you could it might give you the ability to manipulate them better just because you could take it off.
Yeah.
So just a thought for you. Now, which way would you put the camera?
It would be having to face down, so I'm trying to figure out how we're gonna do that. But if anything, we're trying to make a small camera. If it was part of the lid, it'd be on it where the leg
Sure.
would protect it, basically.
Well, consider if you've got 4 legs, that means that you could put your camera right in the middle.
Yeah.
And then now you've got those, you said chains to be able to, that you'd pull on to compress them,
Yeah.
right? They'd be out of the way of that camera. So that's actually not a bad idea. Does that make sense?
Yeah.
Okay. Now, what else do we know? Okay, so consider how many times could I throw this up in the air and let it hit the ground and it's still good?
That's what so we're gonna think about that with the thickness of the walls, but we want it light, so I would say like good
Well, and what I'm asking is, if you've got a plastic container like this,
Yeah.
I can kick that around for weeks and it doesn't get damaged, right?
Yeah. So a plastic container would work.
What about a peanut butter jar?
Peanut butter jar? Maybe. Yeah, that'd probably work too.
That's not bad, right?
Yeah.
Okay. Okay. So what do you know about cameras?
Cameras, most of them, I just know that they all take pictures, have lenses and all that.
Okay. How about this? If you write this down, Spark Fun. Okay? Spark Fun.
Spark Fun?
Go if you go to Spark Fun website, you can look up cameras and see what kind of stuff you can do with them. Is that all right?
Yeah.
I think you can find cameras for like somewhere between $7 and $13 or something like that.
And you should ask your teacher because he might have one. They did a nanolab, plants growing in a nanolab, so they could have cameras still.
Yeah.
And I know you have Arduino boards.
There you go. Those might help out. And also, if you go to SparkFun, if you look up, let's say you decide to use Arduino and this camera or whatever, they will have the computer code for how to run those things. Does that make sense?
Yeah. So
Yeah, so you have to look at the Spark from documentation and see what they have for programming whatever camera or Arduino you're interested in.
yeah. So we're okay. All right. So
Yeah, you have a
All right.
Raspberry Pi too?
Yeah.
Is that
we
what
have
Scott
a
said?
board, like we did lights and everything.
Yeah, I thought
Yeah,
you.
yeah. That sounds great. Okay. What other, do you have any thoughts or questions for us?
um what do you think we have to improve on? I want to look at the problem. So if we're talking about legs, let's say like how many would you say would be necessary? Because I was thinking like 3 would work too, because it'd still be in the middle of the camera.
I'm okay with that.
So and any shape would be fine.
Yeah, whether you go with 3 or 4 or 5, I think those are all good options. And which one works better for your design, I'm gonna have to let you guys decide that, but I think that could work as well.
Alrighty. So if we're talking oh wait, we already solved that because of the container it has less weight because of the
Okay, here's another thought for you. So like you said, you're missing that spring. How, I don't know, sometimes I've seen people having like a mattress or something like that gets left out, or it because
yeah.
there's springs inside the mattress.
Yeah.
Would and sometimes they have a couple of different sizes. You might check to see if that's available, and that might be a cheap way to find a couple of different springs as well.
Oh yeah. And our other solution was to just create like a bunch of different legs, but make them all different because we have like 3 springs, but they're all different. So we were just trying to figure out the height and everything so we could make them the same length of the base. Basically.
Yeah, that makes sense. No, I think that sounds like a great idea, guys. Now, the hard part is you've got to be able to come up with a way to compress each one of those legs.
Yeah.
And so start thinking about how you want to do that and what kind of motor you might want. And you might find like a geared motor that can do that on that SparkFun page. Or your teacher might have some. Okay. It's worth asking and thinking about it. Okay.
Okay. Yeah. Okay. Anything will work. Yeah, so we do have some of those, and if we're so our whole problem that we're still trying to solve is how we're gonna make it land. Because if it just jumps up and we don't know how it's gonna land on surface, unless it's just gonna fall down. So that's our whole problem
Sure.
we're trying to figure out.
And that might be related to how you shape your robot, right? Consider if you have some long wires sticking out from it, if it lands on the side where one of those wires is sticking out, it might be able to bump it into the right position. Does that make sense?
Yeah. So
and other thoughts could be, I've seen some students that make it kind of like the top of it is kind of a ball shape. And that way, if it lands on the top or something like that, it kind of rolls it over to the legs somehow.
Oh, okay, so rolled body.
Okay. Imagine if the top half is a ball and the bottom half has your legs. If it hits the top, then it'll maybe roll over to those legs. Does that make sense?
Yeah.
So I wonder how a turtle rolls over if it lands on its back, which kind of is a semicircle. How does it manage to get back on its legs?
They got to kick a lot, probably.
So that's mostly most of the questions we have right now, and
Okay.
yeah, we're just trying to figure out. We like need 4 different motors for the 4 legs probably, unless we somehow
Maybe. And you might look to see, maybe you can do 2 of them at a time,
2 of
right?
them at a time. Yeah.
Sure. I mean, you put two of those on one motor, and then you put 2 on the other motor, maybe. But these are just thoughts. You might have a better way to do that.
Oh yeah, that makes a lot more sense because I'm still trying to figure that out. So that probably be our main idea.
Sure. And one of the toughest things here is trying to keep your weight down, because if it gets heavy, you can't jump, right? So you got to think on that. All right.
Yeah.
And you don't have to jump 10 feet. You can jump 3 feet. Between
3
3
feet
and 10 feet is good.
Like 30.
Yeah.
Oh, okay. Yeah.
Because your classroom, if you jump 10 feet off a table, you would hit the roof,
Yeah.
the ceiling.
So yeah, we're testing that out with that one we had outside, and that's how far I jumped. But now it's gone, so probably 3 feet will work with the smaller ones we're trying to make.
Avon, what was in your hand that was pink? You can't. I couldn't really
This
see
is
what
our
you were
other
holding.
small prototype, but it kind of messed up. But
Okay.
this was our official size. We're trying to make the legs like a lot smaller instead of like big as these ones, so it could have less weight.
Yeah, that's smart.
Well, and part of it is, one of your heaviest things is going to be your springs, right? Because it's all steel. So you're looking for ways to get as much out of those steel springs as you can, but still save weight on some of those other components as well.
Yeah, so we're trying to like make these springs smaller, or either just either if we could find a smaller one, because we found like different ones.
No, I think that's smart. Okay. Good idea, guys.
Thank you for working on that. Keep working hard on that, because you're off to a good start. Just need to work hard.
Yeah.
Get that robot jumping for me.
Alrighty, we will.
Okay.
All right. Good job,
Thank
guys.
you.
Alrighty, thank you.
Thank
We'll see you
you.
later.
Have a good afternoon there.
Okay. You have
And we
another team?
yes, the last team for the evening, I believe.
Okay.
And it's in Canada.
Excellent. Hey.
How we doing?
Hi, Scott.
Hi.
Bye-bye.
Okay. You probably got another one?
Yep, yeah, we got one more.
Okay, have a good one.
You
All right,
too.
we'll talk to you
Thank
soon.
you.
Uh-huh.
Bye-bye.
Hi, team. How are you doing?
Awesome. I want
Okay.
you to introduce yourselves and tell us what grade you're in.
So we actually have a presentation for you guys, if you wouldn't mind. I would share my screen really quick.
You bet.
Sounds great.
And is it all right if I record this?
No problem.
Okay. Thank you.
So is it visible to you guys right now?
It will
coming.
be. Yep.
There it is.
Lunar jumper.
All right, there we go. So good afternoon. We are from Victoria Park Collegiate Institute in, as you said, Canada. and today we're going to talk to you guys a little bit about our take on the Lunar Jumper project. So over the course of this presentation, you get a chance to meet the team. I'll talk to you a little bit about what we've been doing over the past few months. We'll take you through some of our design processes. We'll give you a look into our current design and what we have right now. We'll talk about some of the drawbacks of our current design and some of the next steps that we want to take. Finally, we will give you a quick introduction into our next design and what we're going to do for the next few months. So we'll get started with meeting the team. Victoria Park actually has 2 NASA HUNCH teams. In this photo, we have both teams combined, but this is just one of the teams. So I'll get started. My name is Armand, and I'm in grade 11.
Hi, my name is Nima. I'm also in grade 11.
My name is Matthew. I'm also in grade 11. I'll give you a hint. We're all in grade 11.
Hi, I'm Dana. I'm also in grade 11. I'm Smara. I'm also in grade 11.
And I'm William, and again, I'm grade 11 as well.
Excellent.
Okay, so the challenge laid out for us was to build a jumping robot with a maximum jump height of 10 feet. Jumping robots are an exciting and perhaps underdeveloped tool for the exploration of other worlds, particularly with an eye towards the moon. A couple of key advantages is that they take advantage of low lunar gravity and that they will allow lunar explorers to more easily overcome difficult sloping terrain like craters. Additionally, the ability of the robot to record and transmit photos will help our explorers to document the satellite's surface features. So what this all meant for us in more practical terms was that we needed a robot which was capable of storing energy and then rapidly imparting it into the ground. We needed to allow it to operate autonomously, we needed a lean but capable robotics array. And to make our development process more efficient, we put an emphasis on modularity in our design, which has the added benefit of making the robot easier to repair and easier to maintain on mission.
Okay, so here's a quick design timeline on everything we've been working up to so far. So at the start of September, we started meeting each other and holding more frequent meetings, and this way we could build team rapport as well as be introduced to our initial design. In mid-September, we all started pitching ideas and putting together anything and everything that we could. Using little aspects of everyone's ideas, we were able to organize our thoughts and ideas through a process that will be later mentioned by my team. At the start of October, we narrowed down our design and we also started ordering parts. This included our 3D design process as well as our 3D prints and our wiring diagrams. And then from mid to late November, we started the building process, putting together all the electronics as well as the box. And to now, where we want to present to you our current design and everything we've worked on. Okay, so for our design process for our prototype, as Mara mentioned before, we work using step-by-step elimination and rapid iteration processes. We started with no fixed concept, just testing ideas, ruling out what failed, and refining what worked. Our very first design was very simple, a suspended box held by 4 ropes and a central spring. Pulling one rope tilted the system, and when released, the tilt and spring tension created controlled movement. That early model helped us understand how motion and directional force behave in a microgravity-inspired setup. Now, my teammate Nima is going to mention more about our current design, but furthermore, it's regarding a modular and more programmable and more far controlled than what we started with. And as a result of lots of testing, feedback, and continuous refinements.
So our current design, or design 1, is literally just a box on springs. We 3D printed 3 layers and put a set of electronics into it. So I'll start from the base of our box. Our base of our box is just a 3D printed square, I'm pretty sure, which has 4 notches, which attaches 4 compression springs, so another 4 notches on the bottom of the box right here. If you can, I don't think you can see that, but. And then we also have a little hole in the base piece, which allows a rope to go through, and it goes into our box through another hole and is knotted to a spool. So this is essentially allows us to pull on the rope to compress the springs, and then if we release the rope, then it will quickly release the springs power, and it will launch our robot up. So that's basically our way of getting the robot into the air. So next, I want to talk about the electronics, so the wiring diagram right here. So in the middle, we have the Arduino Nano, which is connected to two servos over here, if I do this right. And then we have a buck converter right here, which is connected to a terminal block, and then that's connected to a LiPo battery, which basically powers our whole robot, allowing us to actually have launch. And then we have the terminal blocks connected to an H bridge, which is connected to a stepper motor. This stepper motor is important for us because it allows us to have mechanical rotation. And then I just want to quickly go over the Arduino Nano, as it's the most important part of our whole electronic system, as it's basically the microcontroller or the brains of our electronics. As if when we put code through it, it will essentially let our robot actually function, and we can give it like commands to do like pulling on the rope to compress the springs. Moving on, I want to talk about the weight of our design. So we estimate our weight to be around 700 grams, which is more than we wanted it to be. And we think that we can reduce the weight of this substantially, honestly, because we are being pretty inefficient with this current design in terms of the weight. For example, our motor is 0.5 kilo, which is far too much than we want it to be. And it doesn't even give us a good amount of power. And then this is leading me to our observations and more actually problems with this design. So I already talked about this, but it's way too heavy. We could definitely reduce the weight and make it more efficient. Next, I'll talk about it has an insufficient power to mass ratio, which basically means looking at our robot's weight, we do not think the amount of power it can generate from the springs will be enough to send to the ideal height that we want to reach of 7 to 10 feet. And finally, it is way too complex, as we have too many parts inside that are just moving around, too many electronics. And if you look inside, it's very messy, and you also won't be able to tell what's happening in there. So we think we make them more neat.
Yeah, so far, this is what we've done so far, and now I'm going to be going over the next steps that we're going to go through in the following months. So to start, my teammates have already mentioned that we're really focusing on modularity, and we're going to try to focus even more on that by consolidating our design, and which will allow us to fix the prototypes more easily and update it as needed. We're also going to try to simplify the design. As mentioned by Nemo over here, our design currently is really complex and quite heavy. So we're going to try to simplify the design and cut out the unnecessary bits and parts that we can. So that way we can reduce our mass and ultimately increase the force that is outputted. And then finally, we're going to try to implement mechanical advantage in the form of utilizing torsion springs instead of just regular springs. So this is going to be in the form of a hinged knee mechanism, which Armand will be going over right now.
So taking into account all the things that all my teammates have said, this is what we've come up with for our next design. It looks quite a bit different from our first one, but in reality, there's a lot of elements that are shared. So right here in the center, you'll see the hinged knee mechanism that my friend William here was talking about a little earlier. So in the center, you have a torsion spring, and on the top and bottom on both sides, you have, we'll call them the two halves of the leg, right? We plan on using carbon fiber rods or some other material that's very strong for these, because obviously they'll be going through a lot of wear and tear. At the top here, this is our consolidated box, as William said. We want to focus on keeping electronics to a minimum, keeping wiring to a minimum, just making things easy for ourselves and easy to assemble, really. This design will only require 2 servos compared to the 2 servos plus the stepper motor that we had in our first design. The first servo will sit right here at the top. It'll control the small gear, which will rotate these 2 gears. These 2 will then counter-rotate, which pushes the legs outward, but also has the added effect of pushing them downwards as they're connected to the knee, let's call it. And we also have gears at the bottom here so that the bottom halves of the leg can rotate. So that brings us to this position over here. So this is the torsion spring, an example. And it brings us to this position here. Ideally, we want it to be even more compressed. And then eventually, when the servo lets go, let's call it, lets go, we can then jump, right? And our second servo, I mentioned there were two, will basically act as a pendulum. This is something that we're dragging and dropping directly from our first design, and that will allow us to control the direction of the jump. Now, something that isn't very clear in this diagram is, number one, we're going to have, I think, even a wider base than what's pictured here. This means that even if our robot tilts a little bit, it doesn't mean we land on our side. And another thing to aid that fact is having the pendulum a little lower, maybe even on the base of the robot, which is what we're thinking about right now. And what that means is we keep our center, sorry, not our center of mass, but we keep the change in our center of mass relatively low. And that should prevent any awkward tilting, which would, again, cause us to land on our side. Other than that, we are keeping most things the same. So again, we'll be using an Arduino Nano as our microcontroller. And with that, we're going to conclude. Do you have any questions for us?
Sounds good. I got lots of questions. Do you have something to show us first?
Yes, we do.
Let's see that.
Stop sharing.
Okay, stop sharing.
There you go.
So in order to better demonstrate this to you, we do have it in a few pieces.
That's okay.
Otherwise, as Nima mentioned, it is a little bit messy.
That's all right. That's what prototypes are.
So
now you said you're looking at about 700 grams. Is that right?
correct. Yeah. Yeah.
Okay. And you also said that your motor was somewhere around about 500 grams. Is that right?
Yes. Yeah.
Okay. So, what? Now you're also changing the style a lot. So do you think what about that motor means do you need that big of a motor?
So one mistake I think we made with this one is with these springs here. Sorry, I don't know if you can see them. These springs are incredibly stiff.
Okay.
Based on some of the calculations that we did, we kind of figured out that we need either extremely long or extremely stiff springs. So if they're long, then obviously they are stiff. We don't want a robot that's like, I think we calculated it would be around 30 centimeters long, the springs, which would mean our entire robot becomes almost 40 centimeters long. And obviously, the taller you get, the more difficult it is to balance, and you get a bunch of other problems.
Sure.
So we decided to go with stiffer springs. What we found was that as you make the spring shorter, you get a stiffer spring. You need a significantly more powerful motor to be able to compress it. And this motor right here, I'll show it to you. Kind of stuck in there.
Oh, wow, that's cool. You've got a lot of modularity there. That's pretty impressive.
That's definitely something we aimed for, because obviously to deal with one small part, we don't want to have to take apart everything like this. I mean, obviously this is just for the demonstration. So in here is the stepper motor that we're using.
Oh, wow. Yeah, that's a big motor.
Yeah, so it's much bigger than we thought it would be.
Okay.
But even this, we don't think is actually enough.
Okay.
So basically the conclusion that we're coming to is that just putting springs and motors together isn't necessarily the best solution, which is why we're thinking of some kind of mechanical advantage. So that's something I discussed earlier with the hinge knee mechanism, and especially with torsion springs, because we found that for a design like that, or for designs in general, they tend to be a little bit more efficient.
That sounds okay. And I don't know about efficiency of different springs. So obviously a rat trap, what kind you're looking at something like these?
Exactly. Yeah.
Okay. And these would work great for where you're talking about. I think that's a good idea. Okay. And I gotta be careful so I don't smack my fingers here. But that's also a cheap place to go if you want those, right? Now I've seen people that have put they were talking about putting them both at the knees and at the ankles and at the top. So you have lots of options for how you want to do that. Does that make sense?
Yeah.
Now, I think that you could probably go with a much smaller motor if it was a geared motor.
Mhm.
And that way you'd be getting that mechanical advantage that you were thinking about, but it happens slower. There's no reason why it has to jump every 10 seconds. If it can jump once every 2 minutes, I'm perfectly happy. Does that make sense? So I like where you're going. I think you have some nifty ideas in what you're doing there. Now let me ask you, what else in there is heavy? What else takes up some of your mass?
So after the motor, the second biggest thing right here is our battery.
Sure.
Other than that, the rest of the electronics are actually pretty light. And I would say these 3D printed parts are heavier than all of our electronics combined.
Wow. Okay.
Battery. And that comes down to the amount of infill we use, which actually wasn't even that much. I believe the part with the highest infill is right here, the base plate, because that's directly in contact with the springs.
Sure.
The rest of our design, other than the motor and the battery, is actually pretty light.
Okay. And one other thought that might help out a little bit is having shorter wires, right? Because you can imagine the copper and that plastic can also be a significant amount of mass. And I see that you've got some fairly long cables there, and that might help out. Just that long black one that I see up top looks like, is that right?
This guy right here?
Yeah. And it's more about the messy that you're talking about as well. But I think you guys are right on top of it. Now, I'm going to show you something else just as a thought. Whoop, there. Okay, I don't know if you guys were watching with the last team, but I pulled out like a canister. So this is a jar for nuts. And this one's rectangular, and it's similar in volume to the one that you've printed. But of course, if I was to toss this around outside, it would last quite a long time from kicking and whatever. So just some thoughts for you. There might be some already existing canisters to help you out with some of that strength and being lightweight. Does that make sense?
Right.
And don't get me wrong, I like where you're going. I like how you made that come apart and how you had some separate locations. I think that's really smart. So you've got a motor to tighten up to compress your springs. What's your method for releasing that tension, that compression?
So right. Obviously a stepper motor is not very fast, so we can't count on just it unwinding. So the solution that we kind of came up with was having a servo like this, and it would have something on it as kind of a clamp, right? It would hold that rope in place while the stepper motor would unwind. And then that would mean that the rope would only unwind inside the box, right?
Okay.
It wouldn't release the tension on the springs. And then when the servo unlatched the rope, then the springs would be able to release, and that tension would be released all at once.
Okay. And so you're still looking for some kind of a mechanism that's going to help you do that release. Is that correct?
So for our newest design, that mechanism actually, we don't really require it because these servos, the issue is with the stepper motor is that it unwinds quite slowly. These servos unwind really quick, especially the ones that we plan on using. And that means that even in some of the examples that we looked at, we don't necessarily need a latching mechanism. If that becomes a problem though, I think we could just figure out a way to stop the gear and then go from there.
I'm okay with that. I've mentioned to a couple of teams how I don't know if any of you fish. Do any of you go fishing at all?
I fish.
You fish? Okay. And consider, come over. So when you're reeling in the fish, right? You've got gears, and it's kind of like when you're tightening up the spring, okay? Then you want to cast. So you flip over the bailer bar, and now you give a cast. Well, that's exactly the same kind of mechanism as what you might be looking for here. Now, there's a couple of different fishing style reel methods for there. So you can look that up online and they might show you what those mechanisms are and how that works. Does that make sense?
Yeah, that's a good point. That seems like a useful starting
And
point.
so, and that might be a way to use, there might be a way to use your servos that you're talking about in the same way that the fishing reel, um, it'll wind up and then you need a servo maybe to flip the baler bar. You see the idea?
Yes. Yeah.
I think that you could use the same kind of mechanism, but it might, and you can automate it without too much trouble. Okay? Just not a requirement, just something to help you out in terms of looking for another option. Okay?
Yeah. That sounds good.
Now, what kind of, did you say an Arduino or a Raspberry Pi, or what were you guys using?
So yeah, we are working with an Arduino. We started with a Nano, as was mentioned in the presentation. The thing with Nanos is they kind of tend to be a little difficult to work with. These Unos right here are way easier. So for our prototype phase, this is actually what we've been working with.
That sounds good. And do those handle, what kind of camera did you want to use? Do you have one that works with that?
So yeah, this is an ESP32 cam right here.
Excellent. Okay. And that plugs in, it works easily with your Arduino?
Absolutely, yeah.
Okay. And I don't know if you guys know, for some of that stuff, you can go to a website called SparkFun, and it has a lot of the computer code for each of the pieces of hardware that you've got. And all you have to do, you go to the documentation, and it'll help you find it. It already have the Python or the Arduino code that you need. Does that make sense?
Mm-hmm.
All right. Now, so with the box that you've got and the springs that you've got, if you just push it down, does it jump?
So another thing with the fact that these springs are so stiff is they kind of end up just bending a little bit. So that's one major problem that we're facing.
So have you thought about how to fix that?
One of our initial ideas was to have some kind of collapsible 3D printed piece in between the box and the base plate that would allow for the spring to have some kind of support. But then we realized that this design has quite a few other problems, and then we've transitioned to just fully working on design number 2.
Okay. Well, consider, what if you had like a rod that went right up the center of your spring, and the rod could go into the bottom of your box, and it just means that you lift your electronics up enough so that you don't have those rods don't make contact with the electronics. Does that make sense?
Yep. Yeah.
Just a thought for you. Now you'd also want to make sure that you lubricate that, because you don't want the spring to be rubbing on it every time it goes down and comes back up, because you'll be losing some of that energy. So you might look at either sanding that down and or putting a little bit of like a Vaseline or some kind of a lubricant on there. Does that make sense?
Right.
I like your ideas. Let's see, other thoughts. Another thought for you. On the other project, on the other idea where you've got the torsion springs, right? Is it possible to move your electronics package so that it's inside of the legs?
An interesting idea. Just trying to think of how we would do that. It becomes a little bit more difficult because, first of all, that package is now suspended between. I guess it's possible, but I think it would actually work against us because having some mass on the top would make it easier to jump, wouldn't it?
Yes. As long as it's above the center point, I think that you're going to have it's going to help. You're going to have the mass momentum taking you up. If you were to put it down below, now you don't have as much mass giving you momentum going up. Does that make sense?
Yeah, right. Yes.
So, but how about this? If it's like this, imagine if you might be able to get it a little bit higher up by flattening it out a little bit. Rather than having it this way, see if you can position it this way, and that might give you a little bit more of that height that you're looking for. Make sense?
Right. Yeah.
So again, I'm just trying to throw out ideas, and if you like one of the ideas, you don't have to use any of them. So okay. Any other thoughts or questions we can help you with?
I think other than that, we have it pretty much sorted. Oh, in terms of testing these robots, how is that going to work?
Okay, so to keep it obviously, if we were on the moon, you'd be jumping in dirt and having rocks and all kinds of things. Okay, however, that's going to be complicated to set up every place that we go. So the better answer is I got like a moving blanket. I just went to the hardware store and I found a moving blanket, like what you'd use if you're using, like a U-Haul or a Penske or something like that. And I put a dimension in there. Look that up. I want to say it's 80 inches by 60 inches or something I can't remember. And just lay that out. And the idea is that you will jump once, take a picture, jump a second time, take a picture, and that would be considered that's the test platform. Does that make sense?
All right. So I asked that question because we've been thinking a lot about self-righting, and obviously the moon isn't a flat surface. So if we do end up landing kind of sideways-ish, we've been thinking a lot about how we would get back on the base of the robot.
Yeah.
So yeah, I was just trying to get a feel for how much we would need to focus on that.
And it's important because you're not going to get that second jump unless you can get it to right itself.
Yes.
Now, that's also part of why I was suggesting that you put it in the middle lengthwise like this. Because it's long, if it lands on its side, it's a little bit closer to being in its upright position. Does that make sense?
Yeah.
Now, when you compress it, right, you're making these knees go out further. Now, if you had something like, and I don't have anything like, imagine you had a couple of pieces that are on the opposite side. So here's your knees. If you have a couple of flexible like fiberglass, right? As your knees get flexed and it's on its side, those fiberglass pieces, they would also get pinched, and they could reposition back to the front, back to the foot of your jumper. Does that make sense? Hold on, let me see if I have one so I can talk about it.
So you might also think of you got a square or a rectangle there. You might want to change that design a little bit so that it could roll over a little easier. It's hard to change from one side to the next, but if it was more rounded, it might be easier to roll over.
So here I've got like a zip tie. Imagine if you had like 4 zip ties on your one with the knees, right? And if I had 2 on this side and then 2 on the opposite side, as your spring is being as you're making your knees come down, this would do the same thing, and it would push your robot to the up position. Does that make sense?
Yeah.
Okay. So again, just thoughts. You guys will probably have something better than what I have, but I think you guys are on a really good path. I think that you'll be able to find some really good ideas within what you're doing. All right.
Thank you so much.
And
You bet.
even when you test it on a pad of some sort. Don't put your camera in there necessarily because you don't want to ruin your parts.
Yeah,
So wait
start
till you're
jumping without all
sure.
your electronics.
Electronics, yeah. And then you can add slowly, one thing at a time. You don't want to
Yeah.
ruin it.
That's a good idea. All right.
Awesome.
Other thoughts or questions?
Some good starting points.
Okay.
Well,
Good.
you're on a good route there. Do you have another team that's doing jumping robot there?
No, they're not doing the jumping robot. They're doing the trash ejection system.
Yeah.
Oh,
okay.
okay.
That's what
Excellent.
I thought. And that's another day, right?
Yeah.
You come another day. Awesome. And you
Excellent.
can always ask us questions. So keep up the good work. That looks really good.
Thank you. Thank you.
Okay.
Well,
All
thank
right.
you
I'll
so
see you
much.
guys later.
Yeah.
Bye.
All right. Bye-bye.
Bye-bye.
Have a good afternoon.
You too.
Okay.
Bye-bye.
I'll see you later, Flo.
All right. Thank you so much, Glenn.
Bye-bye.
Bye-bye.